So we're going to continue with the Mars recent environments. And first we have Luca Lange. Take it from here.
Thank you for this introduction. So hello everyone. This afternoon I want to talk about the CO2 cycle and the recent evolution of the CO2 cycle. We have discussed a lot on the effect of radiative active clouds on the formation of water ice and the surface and so on. And today I'm going to show that it has a strong effect on the past CO2 cycle. So it's after lunch. Let's start slowly with the basics. What I mean by CO2 cycle is the seasonal condensation and sublimation of part of the atmosphere, around 30%, forming the seasonal ice cap, as shown on the top figures, for instance. And the condensation and sublimation can also be measured on the pressure cycle. On the bottom panel, you have the function of the solar longitude L sub s on the x-axis, the evolution of the surface pressure on the y-axis, and you see this seasonal curve with two drops, which is consistent with the formation of thick seasonal ice caps. The condensation and sublimation also has impact on the surface, with, for instance, the formation of carbonic geysers during the sublimation of slab CO2 ice, potentially forming dark spots. Also some features intriguing at the surface, like spiders, and also you have the pretty active CO2 glaciers at the South Pole with the Swiss cheese terrains, sometimes condensing, disappearing, and so on. And more recently, CO2 ice has been proposed as a mechanism to trigger the formation of gullies, these enigmatic features that we have on some crater slopes, as Bethany showed earlier this week. That might be related to liquid water, but some authors, based on the current activity of gullies, propose that the formation of CO2 ice at the surface and then its sublimation could trigger these enigmatic events. Yet, when we look, for instance, at the formation, at the distribution of gullies, which are represented here by these gray dots, and the distribution of seasonal CO2 ice on pole-facing slopes, which is represented by the colors on the graph, blue is thin frost, the red part of the thickest frost, then it appears that we don't have a perfect correlation between where gullies is found and where CO2 ice is forming today. So this is based on a model output and also some observation of CO2, pretty ugly. Some observation of CO2 frost using infrared or visible imageries show that there is not a complete overlap between where CO2 frost is formed and where gullies are formed. So therefore, you can see actually two views on that. Perhaps, yes, not all of the gullies today are found where CO2 frost is found, but maybe because of the internal variability, because that it takes a long time to form, maybe it's actually formed in recent past. Or maybe these gullies are formed during past, when the CO2 cycle was more intense. Because indeed, when you have a clear view of what happened in the past of Mars, so here's a sketch from Forget et al., we know that when the obliquity of the planet was lower, then we had thinner seasonal ice cap, but more thick perennial ice cap forming because of the atmospheric collapse. But at higher obliquity, these authors have proposed that we would have more extensive seasonal ice caps because of the lower illumination. For instance, this result has been shown by Aberle et al. 2003. Here I show the seasonal evolution of the surface pressure. I remove the mean annual pressure, and I will present the past CO2 cycle as thought previously. When you go to an obliquity of 30 degrees, while the margin of present-day seasonal ice cap, which are represented here by the red curve, and the margin of the seasonal caps at obliquity 40, so this is a gray area in both hemispheres, are quite consistent with each other. It's almost the same as today, and as you can see on the CO2 cycle, it's almost the same. But when you go to 45 degrees of obliquity, the caps are more extended by 10, 15 degrees of latitudes. They are thicker, and therefore the CO2 cycle is more pronounced. We have an increase of a drop of the surface pressure, meaning that the seasonal ice cap are thicker. And at 60 degrees, it's even worse. Caps are really more extended, and the signal and the seasonal pressures is indeed more pronounced. So how these results are found? Well, let's do the thought experiment. So we consider the surface. We are in the polar night, so we do not have solar illumination. We have an infrared flux coming from the thermal emission by the atmosphere. And then you have the radiative cooling at the surface, which is around 30 watt per meter square at the condensation temperatures of CO2. And give us these energy inputs, then you can have the formation of CO2 frost as your surface is cooler, as your surface cool because of this surface energy budget. Yet, because we have a lot of subsurface water ice on Mars, as exposed, for instance, by the Phoenix thunders, by scarps, and a lot of measurements that we know today, it has also an impact on the surface energy budget. When you have ground ice, as it has a large conductivity and thermal inertia, it will store energy during the summer and release it during the winter. Therefore, you have a strong heat conduction and therefore a thinner seasonal ice cap. This effect has been highlighted by Arbele et al. In 2008, and then its effect on the paleo CO2 cycle has been recently highlighted by David Elad last year, and I won't discuss this effect today. Today, I want to discuss another effect, which is the radiative effect of clouds. So we know, based on the paper by Jean-Mathieu Madeleine in 2014, that it has a strong effect on the temperature of the atmosphere, the humidity, but we don't really know its effect on the surface temperatures. Yet, for instance, today, during the cloudy season, when we measured the temperatures of the surface at the equators, which is shown by these points, and we compared with model temperatures, which are shown with these black curves, you see that we have a discrepancy. The surface temperatures measures is warmer by 1050 Kelvin, which is much higher, and this effect is actually induced by the radiative effect of clouds. So today we have a strong warming during the cloudy season in the equatorial region of Mars. And then, as we have seen this morning, at high obliquity, we have much more clouds, and therefore these effects could be much more important, and therefore might trigger a significant response of the surface temperatures, and this is what we are going to study today, and its relation to the gullies. So to study that, I will use the Mars Planetary Climate Model, which has been described by François and Jean-Baptiste this morning, and as we will look at the effect on the formation of gullies, we have to include these slope microclimates, and to do so, we have invented a parameterization to simulate slopes microclimate within the coarse global climate model, and this is described in my paper in 2023. I run some simulation at present day and past orbital configuration, included the radiative effect of clouds, and I also include the effect of subsurface water ice by computing its position at each orbital configuration, but I won't show it here today. So as Joseph has shown this morning, we have a significant different water cycle during the recent past of Mars. Here you have a present-day water cycle. So on the top, you have a map of the y-axis is the latitude and the x-axis is the solar altitude, showing the seasonal evolution of the water vapor content in the atmosphere. On the top, you can see that we have a peak of water vapor in the atmosphere, which is consistent with the sublimation of the seasonal ice cap, of the perennial water ice cap, and then the water vapor is transported to lower latitudes. And on the bottom, you have the clouds opacity. You see that we have a pulse at mid-latitude, which is the Apollyon cloud belt, and elsewhere we do not have clouds, perhaps in the polar night, but we don't have data here. When we model that at 30 degrees of obliquity, we have first an increase of the global humidity because the pole receive more insolation and there is a stronger sublimation of the perennial cap. And you see we seems to have thicker and more present clouds in the atmosphere. And at 35 degrees obliquity, the humidity increased a lot by, on average, a factor of 30. And you can see we have thick clouds forming in the polar night and also in the equatorial regions. The redder it is, the more thick your clouds are. And just an illustration, on the left, this is the water cycle and the water ice cloud with the radiatively effects of cloud, and on the right, without the radiatively effect of cloud. And as you can see, when we include this effect, then it has a strong impact and it changes completely the result. And this is what showed Joseph this morning. If you want to look at the past climate of Mars, we really have to include this effect. But let's get back to the story. So we have more clouds at high obliquity, and let's quantify the infrared fluxes at the surface coming from these clouds. And these plots show you the infrared fluxes going down to the surface induced by only the water ice cloud, not the dust, just really only the water ice clouds. And as you can see, we have a strong infrared flux at mid and equatorial latitude between L sub s 19 and 180, also during the northern summer, and a strong infrared flux in the polar night, which is by about 40 or to 80 watt per meter square. And if we look now at the response of the surface, what is the impact on the surface temperatures, then we have the warming of the surface by nearly 20 to 30 Kelvin around the cap, but also at mid and low latitude. And therefore, this will trigger a response also on the formation of seasonal CO2 highs. So for instance, here you have a plot showing you the extent of a CO2 ice cap in a simulation without radiative active cloud using present-day eccentricity but an obliquity of 35. So you can see the formation of a CO2 ice cap and the formation of a northern cap, sorry. And this is the same simulation with radiative active cloud and with the greenhouse effect induced by the clouds. And as you can see, first, we have a thinner CO2 ice cap in the southern hemisphere. The cap at mid-latitude between 40 and, let's say, 30 degrees of latitude has disappeared. And finally, there is no CO2 ice cap in the northern hemisphere. Another look at that is when we look at the seasonal pressure cycle, again related to the condensation and sublimation of the seasonal ice cap. This simulation shows you an example without the expected, CO2 cycle without radiatively active cloud, and with radiative active cloud, we see that we have a strong impact. The drops during the southern summer is dampened and reduced, and in comparison, there is no northern ice cap. I took this example using almost the large eccentricity, 0.12, and a perihelion consistent with the southern summer, but we can look at other orbital configuration. For instance, when the perihelion is aligned with the northern summer, then we almost have no CO2 cycle, no seasonal variation, and when we remove any effect of the eccentricity, then there is almost no seasonal ice cap forming. Here, for instance, on the right, you have the case with the orbit without eccentricity, obliquity of 35 degrees. Top is the seasonal ice cap predicted by our model without radiative active cloud, and the bottom show you where seasonal ice cap is forming. As you can see, the seasonal cap has disappeared. I won't go much in detail, but we also look at the simulation when we have an obliquity of 30 degrees, but in this case, the effect is much lower. Like, there is still an effect. The seasonal cycle is a bit mitigated, dampened by the radiative effect of cloud, but it's not so much. And let's go back at the gullies when I told you that maybe they are formed at high obliquity when the cap is higher or not. While using my model and my slope parameterization, I show you here where seasonal CO2 ice should form on pole-facing slope without radiative active clouds. And as you can see, we have a good agreement between where the gullies are formed and where our model predicts seasonal CO2 ice. But if we include the effect of radiative active cloud, then again, as for the seasonal ice cap, the extent of CO2 ice on pole-facing slope is much lower, and thereby you don't have a good agreement between the gully's location and CO2 ice. 30 degrees of obliquity, we have an overall good agreement, but again, it's the same as a present day. And then you have the question whether is it enough to explain the formation of all gullies or not. Dundas et al., for instance, claim that the current activity is enough to explain all the formation of gullies. Other authors propose that you need more CO2 ice and therefore a larger extent of the time. But our results show that it is more complicated actually to have a larger extent of a seasonal ice cap. So I will conclude on that and leave you with my conclusion. What I want you to remember, the take-home message is that before we thought that given when we have a larger obliquity, we have lower illumination in low latitude regions, which will lead to a more extended seasonal ice cap. But our results showed that the radiative effect of water ice cloud is super significant. It changed everything, and actually our view on Mars about the CO2 cycle is a bit wrong. I presented the case for obliquity as high as 35 degrees, but our results show that it's also, our preliminary result, I would say, show that it's almost the same for large obliquity, 45, 50, and so on. And that's it. Thank you very much.
Great. The talk is open for a few questions. If anyone is interested, please come down to the mic. I have a question, Luca. You showed that the greenhouse effect can be 20 to 80 watts per meter squared, and this is much more than without the active radiative clouds. This, I guess, assumes a polar cap source. What would you think can be the difference if you don't have a polar cap source anymore, or a limited polar cap source?
Well, in that case, it depends again on your ice distribution. If you think, for instance, if there is no more ice or there is the lag protected, then you have a result, for instance, by Mishneta 2006, where we have a lower amount of humidity. I guess we would have the same effect as for obliquity 30. This is just my think on that. But perhaps we will have a sublimation from other sources, like water stores in the subsurface, water ice at the surface for the mantle deposits, and so on. So this is a simulation we are exploring, actually. I've conducted some simulation assuming a water ice source at the pole, but also at mid-latitudes, not in the subsurface. And the results are pretty the same as what I presented today.
Perfect. Any more questions? Okay, let's thank the speaker again. And next we have Lonneke Roffels.
Thank you, Aaron. Let's see. Do you guys hear me good enough? Yeah, I think it's fine. Okay. I'm going to talk a bit more about gullies, but I actually first want to pose a new term, which is cryoclastic flows on Mars, because I, after 4 years doing this for my PhD, I'm a bit tired of constantly saying CO2-driven flows, granular flows. So I hope you like this term. Please give me some feedback on it if you don't. And otherwise, maybe we can use this in future literature. So what I define as cryoclastic flows for my presentation for now are granular flows, fluidized, so they behave more fluid than a dry granular flow would. And they are supported by the sublimation of ices, which in this case is CO2 ice on Mars. Luca already showed some great examples, but I'm going to start at the basics again. Martian gullies are landforms where there's an alcove at the top where material is eroded. They have beautiful branching tributary channels that converge lower down on the slope. And then when the material is deposited, these deposits fan out at the bottom of the slope. And for a long time, the resemblance of these Martian gullies to terrestrial versions of these landforms fed the hypothesis that these gullies were formed by the same processes as on Earth, namely water-driven debris flows. And this is a beautiful example of such a powerful mass movement in the Ilgraben torrent in Switzerland. And as you can see, they are big flows carrying large boulders, and they're also able to, over longer periods of time, carve these systems. But on Earth, as you can see, about half of their volume contains water, so that's already quite a lot. And for them to actually be really mobile, it has to be raining in the landscape for days, so that also the sediments and the landscape that they are flowing over is actually quite saturated, because otherwise it loses its water and therefore its mobility. So more than a decade ago now, the leading hypothesis of the formation of Martian gullies was questioned by authors finding present-day activity in these gullies. So there were new deposits on the fans, low-bait deposits with levees. Channels were being eroded onto the fans, and meter-scale boulders were moved. So these are authors like Serena, Deniega, Colin Dundas, and Susan Conway. They found a link to the present-day CO2 cycle, not only because of the recent activity, but also their spatial temporal distribution. And even though that might not be perfect, it aligned relatively well. And then, not much later, the first sort of models, hypotheses were formed by Piloget and Forget about how CO2 sublimation could then cause granular flows to actually happen on the surface, because this is a process that we don't have on Earth. Maybe the closest analog is pyroclastic density currents, but they form from a completely different process. We kind of took these observations and these first models and hypotheses on these cryoclastic flows and took it a bit further and actually tested some of them. So at the beginning of my PhD, we've created small-scale cryoclastic flows in Martian atmospheric conditions. So these are 2 examples of experiments we've conducted in which we release mixtures of sand and CO2 ice grains under Martian atmospheric pressure on the left and Earth atmosphere on the right, and you can see the difference for yourself. So what happens under Martian atmosphere is as soon as the CO2 ice comes in touch with something warm, in our case, the bottom of our flume, it sublimates, and the gas pressure that is created is so powerful that it can push the sand grains in the mixture apart, mobilize the whole system, and create a fluidized granular flow. And what we've also been able to do is that we can actually quantify and measure lots of things about our flow dynamics. And when we analyze the data, we see that our dynamics are actually really similar to water-driven debris flows on Earth. So the internal forces that resist and promote motion are very similar, which also helps explain that these landscapes, or at least the recent deposits in these gullies, are so similar to deposits of water-driven debris flows on Earth. But that was not all, and that's kind of what I want to talk to you about, because one of the big questions for gullies is maybe not present-day activity, but as Luca also explained before, what formed them over longer periods of time? Do we need water in these systems in the past to explain their formation? Or could it also be CO2? And because we don't really know how effective CO2-driven flows are at transporting material in various environments, so various configurations of warm slopes and the amount of CO2, for example, needed. That's one question. And the second is, can these flows actually cause sediment erosion? Because that was a big question that no one has ever tried to answer. So what we did is we actually built a bigger version of the flume that I showed you before. So the flume that I showed you before is 1.5 to 2 meters long, and this one is 4 meters long. And we placed that in the Aarhus wind tunnel facility in Denmark. It's a really long tunnel that's actually used for aeolian Martian research, but we just wanted a big vacuum chamber. So we built the big brother of the smaller flume and repeated our experiments, but then this time with various types of material in the flume chute. So that's the steep part of the flume. And the first question then is, can these flows cause erosion? So what you see here on the left is that there's a dark sand bed actually inserted in the bottom of the flume. And then this is more an illustrative experiment because it shows nice the contrast. So the erodible bed is dark volcanic sand, and then the cryoclastic flow that we let flow over this material is made of yellowish quartzite sand with CO2 ice grains. And then when I press play, you see that this darker material is indeed picked up, incorporated into the flow and transported down. And can I see if I do it again? I can show it one more time. It gets so far that our flume was actually not big enough and the sand was transported over it. So this is 2 meters on a slope of 10 degrees, so it's quite a shallow slope. So this is a really fluidized flow. And when we quantify the amount of erosion, because we have done that, we actually see that these flows, in a way, at least at experimental scale, are currently more efficient at picking up unconsolidated material than similar flows of wet debris flows in our lab with a very similar type of setup. But then the question is, in what kind of environments can this process actually occur? Because we see activity related to various configurations of ice and unfrosted slopes in the gullies. So we see locations where we have ice higher up in the alcove. So you could imagine that granular flows here flow over bedrock, so a or at least hard to erode material. We have configurations where there are unfrosted fans and CO2 frost exists higher up in the gully, so you could imagine cryoclastic flows forming here that flow over this unconsolidated, unfrosted material. We have it the other way around, so unfrosted alcoves with frosted vents, and we have systems where there seems to be frost in all cases. And then, of course, we also have the hypothetical case where granular material flows over slab ice. This is a little bit harder to show on pictures, so I only have the diagram for you. And I kind of want to go through these different environments that we've tested individually, but I don't actually know if I have enough time, so I will start with the three most important ones. So the first one is where we create a cryoclastic flow flowing over, in principle, non-erodible bottom. So in our case, that's just a roughened aluminium bed. So those are actually very similar to the first experiments in the smaller setup that I showed. The second one is with an erodible bed, but the same type of flow. And then the third one is flipped around. So we have CO2 ice and sand in the bed, and then a mix of only sand flowing over. And what you can see is that for both erosion cases, the mixture is actually way more airy. So what we see happening is that flow velocities actually increase when we erode material. It's probably due to the fact that there is more entrainment of either warm material or, in this case, ice, and that means that there's more mixing of thermal energy and the CO2 ice, which makes it probably easier for the ice to sublimate, and therefore more ice sublimates and the mixture becomes even more fluidized. So erosion, in a way, has a positive effect on the mobility of these flows. What we further also see is that the internal dynamics really change. So we only have small surface ripples when we don't have erosion, and it's a shame that the video has passed already, but hope you can remember there are really these gas pockets, these bubbles that give it this airy appearance. But then if we look at the deposits, so this is a view of the sand that you see piling up on the surface with the squares. We see, at least for the case with the warmer erodible beds, that the deposit becomes longer. The center of gravity, indicated with the X, is further away. Center of mass is further away. So the entire system becomes more mobile, whereas even though the third case was very mobile in the chute, so it has very fluid ice, because it doesn't entrain that much CO2, or at least the amount of CO2 in the system is smaller than with the middle case. We lose that gas pretty quickly because it escapes from the permeable mixture, and then your granular material doesn't flow out that far. Looking at the time, I can quickly show the other two, and maybe I would like to actually focus on the one on the left. So the one on the left is a flow of CO2 ice and sand over a bed of CO2 ice and sand. So this one doesn't have as much thermal energy. And what we see happening is that we actually don't have one flow front forming now, but we have two surges, if you look carefully, where the flow velocity is higher. It's probably due to the fact that the only heat source in this experiment is the flume sites. And that then also results in a sort of split low-bait deposit that follows these two flow fronts. So what can we conclude from this? That CO2-driven flows or cryoclastic flows can cause large amounts of erosion of loose material quite efficiently, at least in our experiments. When we do some calculations on the forces working on the bed, so the shear stresses and the impact forces, and we upscale our flows to the Martian gully scale, we also see that it's very likely possible that these flows over longer periods of time could cause erosion by abrasion and plucking in these gully systems as well, both of the bedrock and probably also the latitude-dependent mantle or any ice-rich ground that is present. Thermal energy, the amount of CO2 that's present in the system, and also the topography. So I could not show you this, but we've done experiments at different flume angles, and we see different types of flow efficiencies. One thing that is very clear is that we need two prerequisites. So we don't only need CO2 for these flows to occur, we also need some thermal energy in the environment to actually keep these flows going. And ideally, you would pick up both actually along the way in the entire gully system. And then I hope actually that with further constraining, the environmental conditions in which these flows can actually occur, in combination with the work that Luca also presented, we can actually further constrain the possibility of CO2-driven granular flows in Martian's recent past, and hopefully also explain some of the trends that we see, so the current lack of activity in the north. Thank you.
Great. So this talk is open for questions. Please come to the mic and ask your question if you like.
Otherwise, one note, I would already update this graph now based on what Luca presented, so it's in a way quite nice. I think some of the...
I have a small question. What would be the smoking gun that tells you which of the process is the dominant one in creating gullies?
Yeah, that's a very good question. I've been thinking about that a lot, and I've written some hypotheses down actually in the discussion conclusion of my thesis. So one of the things that we don't really understand yet is how these flows, for example, transport boulders, because we know for wet debris flows, there's quite interesting sort of almost convective cells going on with bringing the boulders to the side. We don't really know if that works the same for these flows because there's a lack of viscosity. So that could be an interesting sort of future study to do. A smoking gun that we could get, but that's currently impossible, is if we could have detailed windows into their deposits. Because what we see with the CO2-driven flows is that the fines actually get expelled. So we have some dust accidentally mixed in with our sandy mixture, and we see that that dust gets expelled. And that's definitely very different from wet debris flows where the fines, so the silt and the clays, become part of the interstitial fluid, so the fluid between the grains, and actually are the carrying matrix of the big boulders. So if we would be able to see sort of horizons of deposits lacking fines, or very little fines, or only fines on the top because of later deposition, that would be the smoking gun. But at current resolution, we can't do that, so we would need a geologist or a rover or a
geologist.
Yeah. You could do it too. You have many skills. ICT, I'm sure you can do it. Yeah, Cherry.
Hi, Samantha Baker, Caltech. First of all, this was really cool work, so thank you for sharing it. I'm wondering if you could comment a little bit on the expected sublimation rate of CO2. I think you were touching on it at the end in the conversation about the thermal energy. But my understanding from your experimental setup is that it's sort of a catastrophic sublimation when it comes in contact with the warmer plume. Does that match what we would expect for like a seasonal CO2 cycle on Mars, to have that kind of catastrophic sublimation, or would it be a more gradual process?
No, it would definitely be catastrophic because it's one or the other, and it kind of aligns also with the very seasonality that we see in gully activity. So we see it happening at like the beginning of spring, and we see it, at least our modeling, and it's maybe a bit crude modeling, but it shows that we need warm slopes and CO2 at the same time, which kind of hints at least at the fact that these two really do need to be together. I have to say that, of course, in our setup, the flume is at room temperature and the ice is minus 120 Celsius, so that temperature gradient might be a bit extreme, but based on our calculations, we don't need that high of a temperature gradient to actually instigate the sublimation, because you need a certain amount of energy to start the sublimation, and you definitely have that in systems where the temperature difference is a bit smaller as well. Yeah.
Thank you so much.
Thank you, super work. I'm afraid I will repeat a comment I've made on Monday morning, but I have a question.
Yeah.
So my comment was to repeat again, because it's often forgotten, that the scenario that we suggested with Cédric Pillanger was that, of course, some the subliming CO2 could fluidize dry grain and move them. But the key point is that if you remove some of the dry grain, because gullies are always over ice table, suddenly the ice table sublimes, and that really is very efficient.
Yeah.
I never published that, but I have a presentation about that I showed some time ago. And so it's very efficient to carve. So my question is, since you mentioned this interesting fact about the boulders, could we imagine that by sweeping, if you want, the dust, we could destabilize the ice table, and maybe that could then destabilize some bigger rocks and explain, contribute to explain the boulder motion.
Yeah, I absolutely love that hypothesis. I think it's a very nice, full cascading geomorphic hypothesis from the start to the end, because I think in general the misconception is that these flows are causing the carving of these entire gullies, which is also on Earth not true. Like higher up in the systems, things move because of thermal weathering on Earth and frost cracking, and then you have rockfall happening, and then lower down where this material gets collected, it starts as a debris flow. So I actually really agree that these flows are so efficient at removing unconsolidated material that if they do that, they expose what kind of ice is there. That will sublimate, probably cause some of the dust in the ice or the material that's left to fall into the gully again, which then probably forms the material for the next season or the next event to happen and come along. Yeah, for sure.
Great. Let's thank Lonneke again. And next we have Suzanne Conway, who will present Maria Kefta presentation.
Thank you. As Erin said, this is work by Maria Keffer that I'm presenting today, who did a master's project with me for 6 months earlier this year. And what she was looking at is what Lonneke has introduced for us, which is actually this dust that she referred to that has been expelled and deposited beside active systems on sand dunes in the Martian mid-latitudes. So this is a very nice picture of a gully that you can see here in a sand dune. You can see the frost on the walls, the pole-facing walls of the alcove, the coldest parts of the system, and you can see a nice sort of hole in the middle, which is probably where that ice and sand collapsed off that wall and made one of these fluidized flows that you can see has deposited this dark material, so the sand material on the surface, but you can also see this orange halo around it, which we think is the dust that's been expelled from these flows. So Maria's project, as I said, was very much focused on dune fields. These are very common on Mars. They have a slightly different appearance to what you might be used to on Earth. They're always this sort of dark albedo color. In color images, they appear very dark blue. And on Martian sand dunes in the southern mid-latitudes, so the study was focused on the southern mid-latitudes of Mars, there are various different landforms. So you just saw on the previous slide the gullies, so these large kilometer-scale systems with alcoves, channels, and fans. But we also have another type of gully that is unique to Mars and unique to these dune fields, which are called linear gullies. Slightly non-intuitively, they're not very linear and sometimes sinuous, but that's not my fault. They're called that in the literature, so don't blame me for the name. We're just going to call them linear gullies, even though they're not linear. Fine. They're very strange. They're just basically single channels that don't change in width on their way down. They can be sinuous, and they are often associated with terminal pits or pits surrounding them, and they have leveed sides to them. They're very strange. Also, on dunes, you have a series of other dark slope features that you see in the defrosting season. I'm just going to call these, for the purpose of this talk, dark downslope mass movements without sort of differentiating them. There are a variety of different types. So this is the context. These are the dunes that she was looking at in the southern hemisphere. This is what she was examining, and she wasn't necessarily paying attention to these, let's say, these features themselves. What she was actually looking for was these halos. So these orange in color images, you get these, after a recent mass movement, you get these orange sort of halos around the dark movement on the dune, and they can appear around flows that occur within the gullies, flows that occur within the linear gullies, and flows that don't occur within either linear gullies or gullies that are just on a sand dune slope on their own and form these sort of dark downslope mass movements. And so this gives you a sort of a different an overview of the sort of wide variety of types of these halos. And also you can see the very bright color on here. This is the CO2 seasonal ice deposits at the very end of the defrosting season. So you can see that these halos are deposited both on the sand dunes themselves and on top of the frost. So what did Maria use for this project? She used 3 imaging datasets, orbital imaging datasets, CTX and HiRISE, which are both on the Mars Reconnaissance Orbiter. So CTX is monochrome at 6 meters per pixel, HiRISE 25 to 50 centimeters per pixel, where you have a color strip down the middle, and Cassis, full width color imager at about 4.5 meters per pixel. Now, the color images are much easier to identify these halos in, but you can still identify them in the monochrome images. They appear as a lighter color around these dark cores, let's say. And so the objective of the study was really just to understand when and where these dust halos occur. And so she did that, and she looked at more than this many images, but she found nearly 1,000 halos. So these are individual halos around individual flows in 20 dune fields across the mid-latitudes. So this is the global map of Mars, and you can see with the little crosses the images where no halos were found, but we looked at the dunes anyway. But the circles are the detected halos, with in gray the possible ones. And so across these 20 dune fields, we have 130 images that have these halos inside. What that means is we have actually, in some cases, we can follow it throughout the season, for example, and I'll show some examples of that later. And most of these were detected in HiRISE, but we do have some detections in CTX, despite it being monochrome, and Cassis as well. One of the really cool things that we found was that one of the questions we had was, well, how quickly are these halos in place? And we were really, really lucky to have 2 images by 2 orbiters taken within 30 minutes of each other. So this is the Mars Reconnaissance Orbiter and the Trace Gas Orbiter. They went over the same place with a 30-minute time difference, and we actually saw 2 new halos, 2 new mass movements happening on these dunes, and these halos forming within 30 minutes. So we know that this is an extremely fast process that's going on, and probably, as you saw from Lonneka's experiments, this can be probably emplaced within minutes, if not shorter. So these are actually extremely rapid, and they're emplaced extremely rapidly. In some instances as well, we have a few examples, a handful of examples where, so in the previous example, if you've got good eyes, you might be able to see in the top panel that there's a kind of cloud being emitted on the middle panel in B. It's so fresh, this particular piece, this particular activity, you actually sort of have a cloud coming off it. So in a few other examples where we didn't have temporal images, we just saw the cloud. So this was just a handful of examples, which shows that these activities were actually happening within probably only a very few minutes of the activity happening. We have a few examples of this. So the idea that these halos are lofted dust is supported by the observation of these kind of clouds of dust settling around these. Another question is, how long did these last? We already know that they didn't last beyond the end of the defrosting season, but one of the objectives of this internship was also to have a look and see how long they lasted in the environment, how good a marker of their recent activity. And we find, within the limitations of repeat orbital imaging, so we have to remember that 30 minutes that I showed you before is exceptional. We get very rare occasions, there's maybe 5 opportunities per Mars year to get images that close together of a place. So most images are taken normally within a couple of weeks, if not within a month. And so given that basis, we find that these halos are lasting around 20 Ls of S. So they're definitely disappearing within the defrosting season. So essentially, once this Mars year's defrosting season is over, they disappear and it resets. So they're a really good marker of this year's seasonal activity. And I should have done the animation, sorry, I forgot that wasn't going. So you can see this is just stepping through Elsevier. You can see the halo has already faded here. This is the same Mars year. And by the time the ice is completely gone, the halo is completely gone. So another benefit of having this complete catalogue of this activity is we can look at exactly the times of year and longitude and season when these are occurring. So what you have along the bottom axis is the season, solar longitude, and across the vertical axis is a per site, but it's ordered by latitude. And essentially what we see is that these are occurring right up until the end of defrosting, and that we have gaps in even though we have CO2 ice in these places, we have gaps in the timing and the distribution of these. And our hypothesis is that basically there's too much CO2 ice for the bottom ones, so we can't get this activity because we don't have enough hot material exposed. And for the top gap, you can see there's hardly any images, so it's probably a lack of images rather than a lack of actual CO2 ice, although it could be that the CO2 ice in this particular case is too thin to cause activity there. To be seen. The other point is that you can see that the activity, so in colors are the orientations, and you can see there's a trend in orientation with the season. This shows that different slopes with different orientations are becoming active at different times. And what Maria has done is link this to the presence of different kinds of ices. So this is where she's done a study on 3 specific sites at different latitudes, and she's looked at so in the different symbols at the different times of CO2 ice, so what the CO2 ice looks like, and she's mapped where the CO2 ice is and when the halos are occurring. So what you can see is that the halos occur not just at the end of the defrosting when the frost has disappeared, but are occurring when there are frosted and defrosted slopes next to each other throughout the season. But different kinds of ices in different contexts. So as Lonica was saying in her presentation, it's not just one type of context that allows this activity to occur. We have many different configurations of the ice and the sand that allow this activity to occur. To give you a more concrete example of this is 2 contrasting types of activity. So on the right-hand side, you have what is very typical of the last activity in the season. That is the very last remaining CO2 ice at the top of the slope. That's probably collapsing due to gravitational processes or maybe wind, triggered by wind, and then that falls down the slope on the hot slope underneath it and then carries on fluidized down the slope, emitting the halo. On the left-hand side, you can see the opposite scenario where it's the very top of the dune that's defrosted, and then that tumbles down the slope, probably encountering that cold CO2 ice. That CO2 ice is sublimating and throwing out the dust that's in the sand that's collapsed from the very top of that dune. So, in conclusion, Maria's work has shown us that halos originate from dusty material lofted by these mass movements caused by sublimation. And because they don't survive very long, once the defrosting is over, they're good temporal markers of seasonal activity of CO2. They can occur on dune gullies and linear gullies, but also on other general slopes. So actually, this seasonal activity is way more pervasive than the landforms would tell us. So that's a really cool thing, and would provide some constraints for models as well. And the where and when they occur is really controlled by the configuration of the CO2 and the sand. And of course, the insulation is playing an important role in controlling this, and so which might explain some of the latitudinal variations. Thanks for your attention, and I'll leave you with some pretty pictures.
Thanks, Suzanne. Thank you, Suzanne. This talk is open for questions. Please come up to the mic. Okay, I have a question, Suzanne. I was wondering if we can use this halo to maybe constrain the process that's causing the gullies. Many people suggesting different mechanisms that form gullies, and I was wondering if you can use the halo or different halo or timing of the halo to constrain the mechanism.
So I think that's one of the possible things we can do, because they're a very good marker of when the activity is occurring, and these dunes are particularly active, so it enables us to really follow them. So the disadvantage with, let's say, the normal mid-latitude gullies is they're active on average once every 200 years. And so that means the chance of catching one just after it's happened is really, really low. Whereas here, as I've shown you, we have a really good chance of catching these in the act. And I think you're right, catching them in the act, and this is something we're trying to do this Mars year with MRO and TGO, is to catch more of them in the act. I think will really give us important insights into how this CO2 sublimation is really working in these dunes, which I think will help us to understand the gullies.
Sounds really interesting.
I'm excited.
Yeah, thank you so much. It's impressive. I was impressed by the 30 minutes image, difference images, but I'm not sure I understood. Can you show them again? Because you comment a little bit.
Yep.
Because in some way they look different, so I'm a little lost. You have frost on the right, frost on the left.
I'm trying to get the person. So here, there's nothing, and here, there's something. So
Okay,
this
so
one here is the same one that you can see here.
on the left, it's Cassis.
On the left, it's Cassis.
Okay.
On the middle, it's high-rise. On the right, it's just a zoom-in on high-rise.
Okay, that was my question. I had missed that. I was comparing the wrong ones. Thank you.
That's okay. That's an easy question.
Any more questions? Okay, let's thank Suzanne again. And next we have Noé Lebec.
Yes, so in this presentation, I will discuss the morphology of steep-fronted ice-rich deposits that we recently identified in the region of Alba Mons on Mars. And I will discuss their distribution, their morphology, and also we'll investigate what could be their potential terrestrial analogs to investigate their dynamics. So I will not have to spend too much time on this introduction slide, as the previous speakers have already explained how the obliquity was defining how ice was depositing on Mars. So today, the average obliquity is around 25 degrees, so most of the water ice is constrained to the polar caps, but this wasn't always the case, and 5 million years ago and before, the average obliquity was around 35 degrees, which allowed the water ice to be redistributed to the mid-latitudes and to deposit in various contexts. So today we observe a lot of traces of this water ice, so mostly in craters, in different forms. And it's really important to understand the chronology of deposition of all these different deposits that you can see that I described it here, so the concentric crater field and all other types of glacier. And because they could give us valuable information about the chronology of the climate at the surface of Mars. So the new glaciers that we identified, I have here two examples to show you and to describe their morphology. And what you can see is that they share some similar characteristics because these glaciers have a lobate forms originating from the pole-facing slopes on the crater. So we are in the northern hemisphere, so the pole is towards the north. Both of these deposits appear to be quite thick, and this is especially very striking on their steep front that you see here at the termination. And I will discuss a lot about this steep front because that is something that is not very common on Mars, and it has the potential to expose actually the internal properties of these glaciers. So once we identify this glacier, we asked us quite a lot of questions actually. And first, what is the distribution of these deposits? What's their origin? And what is their internal dynamics? And also how we can explain the layers that are exposed on the front. So you have here a 3D view, and you can see on the steep front that we see two layers. I will come back to this detail a little bit later in the presentation. And all these questions kind of relate to a larger one, which is how do the morphological characteristics of this glacier relate to the Martian Amazonian climate? So to try to answer this question, we first had a look at the distribution of these deposits. So here you have a map of our study area, and all the points that are shown in red are craters in which we observe various types of ice-rich deposits. And you see that in this area, they extend down to 30 degrees of latitude. And all the blue points are craters that are covered by the latitude-dependent mantle that was already also described in previous presentation, and that is one of the most recent deposits, so it is mantling the topography, and it prevents us to explore further the steep front deposits. And when we add the map of the steep front deposits on this map, and we can see that they are located in the higher latitude crater, so just at the limit of the extent of the LDM, and mostly between 40 and 50 degrees north. We can compare this distribution with climate models. So here you have the map of the net ice accumulation at 35-degree obliquity. It was a paper from Madeleine et al. 2014. And what you can see is that the steep front deposits are found at the limit of the extent of the seasonal ice mantle, which is the gray line. So that is the extent of the ice that deposit and later sublimate within the same Martian year. But also that these steep front deposits are not found within the extent of the net accumulation zone, except these few ones. Which is quite interesting because it raised the question of how this ice accumulated and was preserved over time. And then we look at the detail of the topography of these glaciers, and we planned and acquired IRA stereo images to generate DTMs, high-resolution DTMs, so at 1 meter per pixel. So this work is still in progress, but I will give you some measurements that we did on the example that you have seen on the left-hand side. We measured the slope of the steep front, which is around 36 degrees. So this value is quite interesting because it's slightly higher than the angle of repose of granular material. So this can tell us that the material made in from which the deposit is made is a little bit cohesive. So that is consistent with the presence of water ice. We can also estimate the thickness of the deposit by trying to estimate the topography at the base of the glacier. So you have here a thickness map on the left and a cross-section on the right. And what you can see there for this deposit is that the maximum thickness is around 85 meters. But we have other locations where these deposits can be more than 200 meters thick, which is actually quite huge considering their small spatial extent because they are maximum a few kilometers wide. And we can then estimate also a mean equivalent thickness of 33 meters that can then be compared to accumulation rates to try to investigate the time scale in which these glaciers were formed and to see if it corresponds to one or many obliquity cycles. This is still work in progress. Then we try to focus a little bit on the morphology of the steep front of these deposits. So we looked for this example, and when we zoom at the steep front, this is what we see. So here in these zoom images, you have the top of the ice ridge deposit at the bottom, the crater floor at the top of the image, and that part between the white and the black dotted lines is actually the front of the glacier that is exposed. And we have two main observations here. Is that first, the steep front is intersecting with the surface feature of the deposits. So what you can see there at the top of the steep front is that it intersects the ridges that we see at the top of the deposits, which could suggest that this steep front has been retreating over time, maybe due to ice sublimation. And also what we observe at the surface of the steep front is that we have two different textures, with the upper layer being a little bit more polygonized, a little bit more smooth, and the lower layer appearing to be more rough with many boulders. And both layers are separated by a slightly protruding bed that you can see there and that is marked by the red dotted line. So we don't really know what is the origin of these two layers. Could it be due to two episodes of deposition or to the dynamic processes of this glacier? So that's something that we try to investigate. Then, if we have a look, these are a few more examples, so a few 3D views of some of these deposits. So here you see that we still see these two layers. Here we have a steep front that is around like 80 meters high, and the two layers are around like 40 meters of thickness. This is another example, another 3D view. We still see the two layers. And here, where the steep front is higher, it is around 160 meters, with the lower layer being 100 meters thick and the higher layer being 60 meters thick. So we decided to investigate what could be potential terrestrial analogs to try to understand what's the origin of these layers. So we tried to look for debris-covered glacier or rock glacier that would be exposing like layers on their steep front. And the first site was actually suggested by Constanza Moreno. It's the Dos Lenguas rock glacier in Argentina. It's a rock glacier that has a 60-meter high steep front, and when we zoom at the front, we can actually see two layers. And there is a paper from Ala et al. 2021 that suggests that these two layers are related to the internal dynamic of the deposit with a creeping ice-rich permafrost upper layer that is laying over a steep basal layer, and both layers are separated by a shear reason where liquid water is circulating. We also looked for debris-covered glacier with these two layers, and one of the analogs that we found is these places in Iceland. Same, when we look at the front, we see two layers of different properties. And we went to this place, actually last August, to try to understand what could be the origin for these layers. And we have a few hypotheses, like maybe it could be that the glacier is overriding its own moraine or forming a frontal apron, with the lower layer being the moraine and the upper layer being the glacier itself, or that this glacier could be formed by two depositional phases. So these are the main observations that we did on the field. So first, we observe an ice exposure of glacial ice at the front of the glacier. You see here on the picture that it is layered with tens of centimeters of thick debris and boulders embedded within the ice. That's an interesting observation because it confirms that this glacier is actually a debris-covered glacier, so there is like thick ice underneath the debris cover, and that is the case down to the front. We also observe actually these two layers of different textures nearly all along the front of the deposit. And the front is between like 70 and 5 meters, and no matter the place, we still see these two layers. And if we look at the details of these two exposed layers, we think that the lower one is made of finer debris, and what you see it appears like to be kind of brown here. And the upper layer is made of larger blocks, meter-scale boulders. So if we discuss all the hypotheses that are possible from this layer on Earth, we have these three cases. So the first one was more about the rock glacier that I described before, so a shear zone between an upper creeping ice-rich layer and a stiffer lower basal layer that could be maybe induced by basal circulation or the topography below the glacier. The second hypothesis that we try to explore in Iceland is the building of an apron at the front of the glacier, maybe due to debris untrained by the basal ice, or a glacier that is overriding its own moraine. And the last possibility, it could be that these two layers are bands that are formed with varying debris contents formed by multiple events of deposition and ablation due to the obliquity changes and changes of the climate. All these hypotheses have their limit, and we don't really know what is the best to explain the layers that we see of Mars, but that's still something we are investigating. So in conclusion, we found a new type of ice-rich deposits in the region of Alba Mons. We explore their morphometry, and we have been doing some measurements. And also we compare this morphology with potential terrestrial analog to try to constrain what are the processes that could be involved in their formation and evolution. So we have plenty of things that we would like to do next. We would like to compare the distribution to output of climate models. So I did it a little bit in this presentation, but there are still a lot of things to do on that point. Maybe we could try to date these deposits to see how we can place them in the chronology of water ice on Mars. And later, we will also try to explore the dynamics using maybe numerical models. So that's all for me. Thank you for your attention.
Thanks, thanks, Noé. This talk is open for questions. Please pile up next to the mic. Do you have a question, or you? Okay, perfect.
Hey, Noé, this is a really nice talk. Ali Rutledge at NAU. Have you considered? Does it have a Sherrod track through this crater? Is there a way to maybe internally interrogate the layering?
These are quite small deposits, a few kilometers large, so I don't think that Sherrod will have the resolution to identify the base of the deposit. I don't think that's really possible.
Another argument for a shallow radar.
I have a question. You wrote next things to do, compare the distribution to outputs of climate models. And I was wondering which models do you plan to compare it with, since it's such a small the feature?
Yep. So there are many processes that we would like to investigate. For example, the effect of slopes. So you have seen that this deposit is located within craters that are quite small, and that the deposit is originating from the pole-facing slopes. So maybe the fact that actually the distribution doesn't fit model, for example, for Madeleine et al. Could be due to this effect of slopes, because we can imagine that the steep slopes would be colder and have less ablation due to sublimation, so more able to preserve the ice for longer. This is something that we could try to have a look, and also test different values of obliquity, because we don't really know what will be the best conditions to form this deposit.
Yeah. Let's thank Noé again, please. Next we have Ali Rutledge. Plenty of time.
Great, thank you. So we have half an hour, right? Almost time for coffee, everyone. Right, so I'm going to talk to you today about polythermal glaciation, why it's important, why everyone should care, what it can tell us about Mars, and its climate record. But I first want to acknowledge all my co-authors. A lot of the work that I'm going to show today was done by Candace de Anda and Ian Mars, 2 students at NAU. So, like we just heard from Noé, glaciers are widespread on the surface of Mars. We have features that we call LDA, LVF, CCF, GLF, all the nice acronyms for basically debris-covered glaciers. They're a non-polar, pretty large ice reservoir, widespread in the mid-latitudes. Everything you see here in a color is an ice deposit. So we're looking at that mid-latitudinal ice. There's a lot of radar evidence for these features being pure water ice with some evidence for flow. They've got a thin, so anywhere between less than 10 meters and maybe up to 50 meters layer of debris cover, which is armoring that water ice from the atmosphere and keeping it from sublimating. And finally, these features show things like flow lines, which you can see in this gorgeous DTM made by Sean Doran. Things that look like moraines. We've even got evidence for glacier-linked eskers, like this one mapped by Francis Butcher over here on the right. This is actually, that ridge you see in the middle actually directly connects to a lobate debris apron, or a debris-covered glacier, and looks like it shows evidence for water flow at the base of the glacier and a deposit out in front of it. And I should just emphasize that these are quite young features looking at Mars. I think the largest features date anywhere between 100 and 500 million years ago, and some of the smaller features could be as young as 10 million years old. And we know that glaciers are coupled to climate, and so my major driving questions here are what was the past thermal regime of these glaciers as they were forming and flowing? How much liquid water could have been present? That'll kind of guide our work going forward. So when I say thermal regime, what do I mean? Terrestrial glaciers are divided by their thermal regime. They can either be warm-based or temperate, or cold-based and polar, or split the difference. So when we say warm glaciers, that's any alpine glacier that you could go to in Switzerland or here in France. You would go up to the mountains and see a glacier like the one on the left here, which I've nicely colored red so you remember it's warm. But these glaciers are full of water during the melt season. The ice is at the melting point. That's how they're flowing, they're sliding, they're scraping, they're forming those big moraines. And there's a ton of liquid water throughout the ice, at the bed, and on the top of the glacier in summer. Cold-based or polar glaciers are kind of the opposite. They're frozen to their bed. The ice is below the freezing point throughout. And the water, when it does exist in the system, is generally a top-down melting situation. So you can see in the height of the summer season, you would see water flowing over the top and occasionally making it close to the bed through like conduits in the glacier. And polythermal glaciers are a combination of warm and cold ice, either seasonally or spatially or both. So you've got sort of varying amounts of water in that system and some warm ice, some cold ice. Glaciers on Mars today are almost entirely mostly cold-based glaciers. The surface temperatures wouldn't support a warm-based glacier right now, and we have been observing these things since the 70s and haven't seen any evidence for motion. You would all hear about it if we did. They indicate a recent stable regime. They're frozen to their beds. They're not doing a whole lot right this second. However, like I pointed out that esker earlier, eskers are subglacial melt features or end-glacial melt features. We've seen evidence for scouring. Anna published a great paper in 2023 showing that in the fairly recent past, late Amazonian, we could have had warm-based glaciation on the surface of Mars. Like I mentioned before, polythermal glaciation is a combination of those two. Sometimes it's a seasonal cycling between those two end members. And so my question is, maybe can we test whether these glaciers were polythermal under the recent past climate? And this is my specialty, can mineralogy help us understand that history and help us tell what thermal regime did those glaciers occupy? So we saw a lot of this on Monday, but we'll just review. When water and rock interact, we form new minerals. Aqueous alteration minerals are ubiquitous on the surface of Mars. This is a great map from 2014 by Bethany Ellman and Christopher Edwards. And when I asked Chris for an updated version, he said there wasn't one yet. So get on that, guys. But we know that we've seen clays, amorphous silica, salts, and all kinds of other water indicators on the surface of Mars. A project led by Brian E. Horgan in the past led us to find that there are definitive signals of warm-based glaciation on Mars-like bedrock. Don't worry about too many of the details here, but we went to a couple glaciers on the west coast in Oregon and looked for aqueous alteration minerals in front of them and under them. And we found that you can see opaline silica and silicates deposited in wide enough areas that you can actually detect it from orbital and aerial remote sensing. So my question here is, when you go to polythermal glaciers, what can we see? What can we detect with remote sensing and ground-based methods? So to test this, we went to a polythermal glacier called Storglaciaren in Arctic Sweden. It's marked on the map right there. And this is in a region called Sápmi, which is the traditional lands of the Sami people. Here you can see Storglaciaren, which is Swedish for the Great Glacier. Everybody up there reminds me they're very creative with their names. This used to be the biggest glacier in Sweden. So it's been continuously monitored for 80 years, and we have a really great climate record here. The middle of the ice has been temperate for a long time. The sides, these margins, and the front have all been frozen to the ground. This is a kind of classic Arctic polythermal glacier. You see this kind of polythermal glaciation in Svalbard and all over the north part of Scandinavia. There's relatively low water-rock ratios compared to a warm-based glacier, and this whole thing overlies fairly Mars-like rocks. They're igneous or lightly metamorphosed igneous mafic dikes. They're iron-rich rocks. And we have about 135 years of glacial retreat, revealing this quite large glacial outwash plain, which makes it easy for us to sample up where warm ice used to rest against rock and where cold ice used to rest against the margins, these large lateral moraines. We went into the field and collected rocks, sediments, and meltwater. We characterized a lot of these materials both in the field and brought them back to the lab, and that analysis is still ongoing. We also took a UAV and did multispectral mapping of the forefield. And as well as I said, we did some nice little field spectroscopy as well. So I'll dive right into the results here. On the left, you can see a map of the glacial forefield. Storglaciaren is at the top of the image. You can see the cold margins, a couple of active channels. We've got an ice-cored moraine on the left that actually makes a nice rock glacier. And on the right, we've done a few we're working with all of 4 bands here, so go with me. We've done a few mineral indices to try and highlight some alteration minerals in the scene. Everything that you see that's blue or red is we're trying to highlight iron alteration or iron coatings. And anything in green is us attempting to highlight clays and sort of the clay absorption there in the middle. So you can start to see some patterns right away. We've masked out ice and water and vegetation in this image, so hopefully minimizing input from those end members. But you can start to see some sort of geographic constraints here. Most of the iron-rich bands are showing up towards the edges of the scene, and everything in green is more towards the center. You can start to see some red in the middle, which actually is showing kind of some abandoned stream terraces, which we thought might indicate age and oxidation as things are left open to the air. And so we've gone and sampled sediments and water from this entire area. One of the first things we noticed is that in many places where bedrock is revealed, you actually see some really beautiful subglacial, or probably subglacial coatings.
We observed these in the Cascades as well, and so I was really excited to see them here. These are really consistent with work done by Brian Wally in Norway in the 90s. He found iron manganese coatings in beautiful bands in front of polythermal glaciers. So we think this is indicative of really an oxidating environment happening at the direct ice bedrock contact. And we're doing a lot of SEM and other like deep characterization of these rock coatings. But you can see red, purple, and even some kind of light tone coatings, which we think might be amorphous silica within those coatings. The field spectra showed us some really nice differences between the cold-based sediments, so the sediments that were in contact with the cold-based ice, and sediments in contact with the warm-based ice. And the biggest difference is, hopefully you can see here, there's at the top of the scene is the opaline silica lab spectra and chlorite lab spectra, which we found matched really well with some of our field spectra, which are all shown in black. The biggest difference here is the cold sediment showed sort of the predominant alteration mineral would be that amorphous opaline silica, and the warm sediment showed a lot more evidence for an iron magnesium clay, yay clay, Mars people, and that being chlorite. There is a lot of chlorite in the metamorphosed mafic rocks, so we're doing more detailed work with XRD and such to characterize what's detrital versus what could have potentially formed in situ. And some of the most exciting results are from the water chemistry. This is a traditional method to study subglacial alteration in terrestrial glaciers. And so I'll go through the plot first. I've kind of blocked out the axes to make it a little easier to understand. At the top, you have, this is all water, remember, not rocks. So this is dissolved silica at the top, dissolved cations, so magnesium, calcium, potassium, and sodium in the middle, and dissolved anions at the bottom. So that's looking at things like chloride and sulfate as indicators of sulfuric acid dissolution or HCl. Sorry, somebody help me out, my brain is gone nuts. So we're looking at acidic dissolution on the bottom, sorry. And on the x-axis, you're looking at precipitation, so sort of the what we want to take out of the system because this is not coming from glacial ice, moving into outwash from warm ice versus outwash from cold ice. And I hope you can see that the biggest trend is there's more stuff dissolved in the cold margin outwash than there is in the warm ice. So that tells us a few interesting things here. The major cation concentrations and silica concentrations are highest in the cold-based ice meltwater. Remember, water, not ice. We see here that the dissolution is overall driven by hydrochloric acid and carbonic acid and sulfuric acid dissolution. I need my coffee too. You can also see that sulfuric acid concentrations are highest in the outwash from the cold-based ice, and this is likely due to more pyrite oxidation happening at those margins, which then drives acidic weathering. And we can get into the feedback loops there, but again, more stuff is happening at the margins. We think that you're seeing more effective breakdown of these silicate rocks at the cold margins, probably because there's just less water being flushed regularly. So everything is sitting in contact for longer residence times. It's a more stable environment over longer periods. Right, so our major takeaways here, I moved through that a lot faster than I thought, is that the mineralogy of polythermal alteration varies spatially within a glacial system. It's most likely dependent on the thermal regime of that overlying ice. Our major take-homes are that we're seeing most amorphous silica is most predominant in the cold-based sediments, whereas more clays are found in the warm-based ice proglacial sediments. And again, we don't know for sure if that would, I'm not trying to say clays form under this glacier, it's a really small alpine glacier, but we are seeing clays being broken down out of the rock and left as evidence of that breakdown. We see subglacial precipitates that are really iron-rich. Those definitely, or almost definitely formed under the warm ice because you have to have glacial sliding to form those. And finally, we see a lot of sulfuric acid dissolution at the cold margins. Thank you very much for your time. I'll take questions.
So this talk is open for questions. Whoever wants to ask a question can go down to the mic and ask a question.
Janneke Roelos from Utrecht University. This might just be misinformation or like the lack of information I have. This is, of course, quite active systems that you can visit, and the rocks are there and it's happening. But for Mars, if you want to do this, but then spectrally from orbit, is there enough material sort of in situ, or is there too much dust on top of it that you can still see these signals around glaciers, or you're hopeful that?
It's a really great question. Can we see this sort of pattern on Mars? I think technically with CRISM scale we could. I know a former student of Brian E. Horgan's, Noel Scudder, did an initial pilot study looking for some of these weathering products at glacial-like forms, GLFs, and he found a little bit of evidence for some amorphous silica to be present in those areas. We haven't yet done a detailed survey because I can't get any funding for that study. We've been proposing it a few times, so I might need to find a student who wants to do this. Basically, the short answer is with CRISM scale, yes. With anything else, it's, the GLFs, for instance, you're not going to see these kind of spatial patterns in like a Themis pixel. Thanks, Lannika.
I have another question, Ali. You showed that there's more dissolved stuff into the cold ice rather than the hot ice, right?
In the water coming from the cold margins, for sure.
So a naive question, what does it tell us about Mars?
Hopefully, what this tells us about Mars is that if we look for evidence for this kind of dissolution, so this is again the water chemistry, we're still, this tells us a little bit about what should be happening. We should be breaking down pyrite. Maybe if we had a more evaporative atmosphere here instead of a lot of liquid water moving through, maybe you'd end up depositing sulfates. Maybe actually see this pattern in Svalbard at glaciers just like this, but then when the spring happens, the water dissolves them all very quickly. Essentially, this can help us back out what could be forming in a more Mars-like climate and then what alteration minerals to search for. Thanks.
Okay, let's thank Ali again, please. So the session is over and we go to a coffee break and we'll
Is everyone back? I can hear her. Okay, so please spread the word about tonight, whoever is coming. This time I didn't put a detailed plan and a metro map to go because nowadays, if you type Port de la Conférence Pont de l'Alma, as written down on Google, it will tell you how to go. I wanted to state that I mentioned in various documents that we will stop at 11 p.m., but in fact, the boat will be back earlier. So if you find that it's a little too late, I think the boat will be back at 10:30. So you can leave at 10:30. But meanwhile, the boat will be cruising between 8:30 and 10:30. Okay? So if you have any question, you can ask me later, but otherwise, we all go by whatever means you wish. Even a cab won't be very expensive. It's not that far, so a few euros and to go back to. And then we'll meet starting at 7:45, and then the boat don't arrive after 8:30. The boat will be gone. So the boat is cruising. We will go all the way around Paris to watch the different historical sites. And of course, it will be nighttime, but there will be a lot of light because Paris is the city of light.
have your own mic over there if you want.
Okay, welcome back. I am Scott Rafkin from Southwest Research Institute. I will be your host for the last session of this afternoon. We have 4 talks. The first 3 are related to subsurface ice and water. And then on the last talk, which is the keynote, we'll switch up to look in the atmosphere at more at compositional stuff. And so our first talk is Sylvain Piquet. And did I say that?
All good.
Good.
Perfect.
Okay. See,
I've heard it all.
French is not my 3rd language, so. So yeah, it's a great lineup. The first 3 talks are 13 minutes, and then we'll have time for some questions. The keynote at the end is 20 minutes. Again, time for questions. Since this is our last session, we do have a little bit of time margin at the end if we need it, and you should still have plenty of time to get ready and get ready for the dinner cruise. Okay, Sylvain, please take it away.
Thank you. Well, as you'll see, English is not my first language either. So for this talk, I'm going to present the outcome of a mapping effort by the Mars Climate Sounder team aimed at mapping the distribution of shallow water ice on Mars in the northern hemisphere. So MCS, the Mars Climate Sounder, typically looks at the atmosphere, but every once in a while, regularly, it stares down at the ground, measures surface temperature, the regolith temperature, and we can derive various properties, including the depths at which you might find water ice and the physical property of that dry layer on top of it. So I'll talk a little bit about that. So let's get to that. And just one last point. So you'll see this talk is really discussing this question through the lens of exploration and maybe a little bit less about climate. So it's really a in situ research discussion, landing future missions and landing people in these locations. So a quick repeat. So we have 2 main themes that we'll be discussing in the next few minutes. In blue, prepare for human exploration. And to do that, you want to be able to let our engineers know where they'll be able to find shallow water ice. So tell them where to land to access water ice and what type of equipment you want to bring. Of course, for the selection of the landing site, discuss the lateral variability. So you're ready to know what kind of variation in depth you'll have to encounter within your working area. And the 4th point in blue is also equally important. It's characterized the physical or thermophysical, but the physical property of that upper dry layer that you'll be working on, roving on, that protects, insulates that layer, and that you'll have to dig through to access that water ice. And of course, in the context of this conference, we want to constrain the Amazonian climate. So we're not working in a vacuum. Information existed, but as you'll see, it tended to be a much lower resolution than what we'll be talking about, and highly spatial discontinuous. And to illustrate these points, I have my 4 panels on the right, so there's a sort of a microscopic dimension to this work, constraining the regolith, the microscopic scale to understand the properties of that upper dry layer. There's the second panel, that the scale of the distances that an astronaut will be able to walk around, or maybe a small rover. There's a regional scale, the 3rd panel, to link these different properties we'll talk about with the geology, and there's a regional or global scale on the right. So we know water ice is abundant in the shallow subsurface. In this talk, really, I'm focusing in the top meter or so keep that in mind. And we know that through, on the left, the Phoenix lander observed that water in white right here. So that's one source of information. At a 40 or 50 location, we've seen those craters exposing shallow ice. It's great information, but remember, globally, you only have a few discrete locations. We have those ice exposing cliffs at the top of the image. Imagine you're on a plateau, and then you have that wall of ice, and then it's flatter. Of course, you're not going to land people, or probably not equipment neither, really close to an actively retreating cliff. So that's great, but that's not exactly what you're looking for landing. And then there's, of course, the immense information about the amount of hydrogen in the subsurface. So water ice, whether it's in excess or pore ice, has a uniquely high thermal conductivity, so K, and inertia, I, compared to most typical Martian materials. And for that reason, it has a unique temperature signature when it's present at the surface or the subsurface. Unique with the exception of bedrock, and we'll get back to that. That means that when it's at the surface or in the shallow subsurface, its seasonal temperature trend is recognizable. So I illustrate that with this 3 panel for 3 different latitudes. On the x-axis, you have the season. On the y-axis, the temperature. And you can look at the center panel, the key. Long story short, when you position that high thermal inertia material, the water ice, in the subsurface, you influence the seasonal temperature differently as a function of that depth, but also as a function in color of that upper dry layer material, the overburden. And so you can imagine acquiring temperature, so information at 2 different times, 2 different seasons, phase 1 or phase 2, and from 2 measurements, you could deconvolve those 2 unknowns. One would be the depth at which the water ice is located, and one would be the thermophysical property or the thermal inertia of the upper dry unit. All right, so how do we do that? Specifically today, we're going to talk about MCS, or the Mars Climate Sounder surface temperatures. I'm using specifically the 32, so the B1 channel, 32 micron channel, because it's mostly transparent. The atmosphere is transparent, and the surface has a high emissivity. The spatial resolution, the vertical resolution, is 7 kilometers, so keep that in mind. And we're going to look at observations that we've targeted between 80 north and 30 north at 2 different seasons, so phase 1 and phase 2. Remember the plot I showed you in the previous slide, and we have a view of MCS on the left. In the bottom right corner, you get a sense for why we've designed that campaign. From Mars year 29 to 34 through the usual operation, we got something like 35% coverage with just the very big holes. But when you specifically target at crucially or strategically selected times and seasons that are listed here, you can fill up these holes and generate coverage that's meaningful. So that's what we've done. And the first map we obtained, phase 1, looks like that. So it's temperature from 150, so you have frosted regions at those low latitudes, to 270 Kelvin. So that's sort of input 1 or the map number 1 that we obtained. Map number 2, a little later in the season, so you see the temperature changed a little bit. Scale bar is about the same, got a little colder near the pole. The low latitudes remained cold where you had very low thermal inertia materials, a little warmer elsewhere. And now imagine you take these 2 maps, so those are the one I showed you, you feed them through a thermal model. I'll skip a little bit to save time, and you create for each point a lookup table like the one on the right, where one dimension would be the depth where that high thermal inertia water ice table is located, and one axis would be the overburden thermal inertia. And you can minimize the RMS and identify the best solution for that depth and that dry overburden thermal inertia layer. So output number 1, the ice depth. So the color is how much you would have to dig to find that interface. From 10 centimeter, it goes up to 1.5 meter in this case. So that's the color you see on this map, going from 80 north to 30 north. Where you do not see any color, you see a gray pixel. Typically, that's just the molar background. It means that there was no interface that was found. On this map, you also have the ice exposing craters. You have the surface assets, so Viking Lander 2, around 150 east, and Phoenix. I don't know if I can point. cannot. And ice, no ice exposing craters and cliffs. Oh, so how do I do that? Oh, thank you, sir. And so now we have a map, thank you, a map showing the distribution of this ice at different latitudes. I have a couple of masks. The black mask corresponds to units 6 and 7 in Jones et al. So it's basically the dustiest terrain. They were typically CO2 frosted at some point during a campaign, meaning that I cannot retrieve anything. Good news, you will never land there. This is too dusty, it's not load-bearing. It doesn't match the requirement that NASA set to land. You'd get stuck in there, it'd be a nightmare. The shading corresponds to high ice opacity, at high atmospheric ice opacity, which currently are difficult to treat with the thermal model because, as we've heard today, water ice in the atmosphere contributes a term, a radiative term that is not currently included in the model, and therefore the energy balance solution is not very clean in these locations. But elsewhere, you see where you would have to dig to find this ice. And one of the key findings is that you have the really high lateral variability. So you have a complex story here of deposition and potentially retention or stability of this ice. I went the wrong way. Yep, no, let me go back. All right, so the second output of the model was the thermal inertia of that upper dry layer, and the bottom map is the equivalent or the corresponding grain size. That's an important map for the engineers. You do not want to land where you're not load-bearing. You do not want to land where it's too rocky, and it's questionable whether you want to land in a potentially cemented terrain. This is the kind of product that we use, for example, Matt Golombek uses to sort of degross the work for selecting a landing site. So back to the water ice table, you can compare the map on the right, so the one I showed you was a different projection with different products that exist. The background here is the water equivalent from Mons, and there's some similarities, some differences. But certainly, if you stare long enough, you'll certainly recognize some of the patterns. And you'll also see questionable places where ice is being exposed by craters, and it's not in this map, not sure why, and vice versa, where this map sees ice, and yet no ice is exposed by craters. Sure, different data set, different stories, but certainly something that's it's intriguing, but at the same time, the similarity is striking. All right. I could not resist, I don't know if Bruce is here. Bruce, yeah. Bruce, I grabbed that 2005 map displaying the distribution or the location of ice as a function of different atmospheric vapor content, and compare that to the map just by eye. And there are some interesting similarities that suggest that, you know, at the time of the deposition and retention of this ice, what got capped, maybe we had a much higher vapor in the atmosphere than currently. I'm hearing that it's well known, so maybe I'll move on. Now imagine you grab the water ice map that I showed you, and you mask out the regions where that upper dry layer, the overburden I mentioned, you mask out where that upper dry layer is not consistent or cannot, that does not match the requirement for landing, for roving. And then you get a map that looks like that. Oh, it's a little blurry, but and you only keep the shallowest ice because this is where the signal is the strongest, and this is where engineers are telling us that it's going to be the easiest to access the ice. You know, 0.7 meters easier than 1.5 meter. And when you do that, there's 5 regions that show up as displaying shallow ice, but also a regolith that's accessible by people, rover, and that you can land on. So of course, there's the really high latitude ice. You're not going to land there. This is not in the plan, and so that's something that we can sort of exclude. There's the EL, so the Eastern Lyot Crater region, with relatively shallow ice right here and some ice exposing craters. You have AP, so Arcadia planitia right here. Same ice exposing craters, shallow ice. Those two regions are not conducive to future exploration because they are within the limit of the seasonal cap, which I listed right here. So see this boundary right here? This is the continuous seasonal cap, the continuous extent. So there's even patchier ice that goes beyond this line. So really, this is not somewhere you want to be long-term or for the duration of a mission, just because you're going to be partially covered with CO2 ice. So then you have two more regions. You have PM, the Flegramontis, where you have relatively shallow ice with ice exposed by craters, and Nilosyrtis. Nilosyrtis, in red, is really questionable. There's no ice exposed by craters there. And we've seen maps, I think Bethany, I've seen your maps, as well as Christopher's maps of bedrock. There's lots of rock and bedrock exposed there. And so it's my impression that I'm mapping shallow bedrock in these regions and not ice. And in fact, bedrock and ice have relatively similar thermophysical properties. So this is the main output. So MCS data was used to map that shallow ice. It's a remnant of recent ice ages. This is a lot of ice, which begs the question, how do we get so much stable ice? And that's going to lead to the next talk. When these maps came out, there were some questions about how could we possibly have ice at those latitudes. I think we'll get the answer. We start seeing regions of interest for future exploration that are emerging. And we have another campaign, so it's the second to the last point, in the pipe, due in April this coming year to do a similar work in the south. And an AGU talk, but probably won't be able to travel, so probably not going to happen. Thank you.
Thank you. We do have time for questions. I see Bruce is already on his way down.
Oh, actually, I beat
Oh,
Bruce on the side.
Please, yeah, go ahead.
I wanted to be quick since Sylvain called out my name, Bethany Ellman, University of Colorado. Actually, Nilosyrtis mensae is not in the same region that we're mapping for the most part, the bedrock phyllosilicates, and there's a paper by Joe Levy, 2007, and there have been some follow-ups. There are what look like glaciers and lineated valley fill in portions of that. So I suspect that you could be mapping ice, but in most places it might be deeper. I did have a question, which is, I noticed that we were using, I believe, MCS at 7-kilometer resolution rather than Themis at 100-meter resolution. I'm guessing that's because of the cold temperature sensitivity or something. Could you comment on what you would need to make a higher resolution map? What kind of sensor, what kind of...
Funding?
Simply you can do it with the Themis? I'm actually more going on the lines of if we collected thermal data, say at 5-meter scale or 10-meter scale on Mars, could we do this?
Yeah, so you're exactly right. So funding is always a question. We are working with Christopher, with Luca, with other people, to continue the work that Josh Benfield initiated, which is mapping, doing exactly this type of, you take 2 measurements at 2 different times with Themis. It is complicated right now by the orbit that Odyssey is on, which means you have to rely on existing data. Odyssey is on a terminator orbit. So it's not the best, so we have to work with that, but we can. So generalizing this work is doable. It's not as straightforward as a point spectrometer, where you can query the data the way you want and so on. With Themis, it's very challenging, but we're getting to that, and this is work in progress. We just started. So yes, I would argue that we will need to maybe refly maybe a higher resolution instrument that could do this type of work. And imagine, ice depths at, maybe 10-meter resolution, something like that, I think would be crucial to answer some questions about in situ resource utilization, about relationship to geological objects. At every scale, I didn't talk about that, but at every scale we've been looking at water ice so far, from Phoenix to large scale, there's lateral variability that's significant at any scale we've looked at. So it might be challenging to land people and have the certainty that you'll have water ice accessible. Maybe it's very, maybe wavy. So yes, we'll probably need to fly something. I'd love to. And maybe I should grab your map, so we should look at the reference you mentioned, if I was off. Bruce Jakowski. I was going to say.
Can you get my question?
So back to this map. Oh, no.
Let me give it a try.
This one right here?
My question is related to what you and Bethany were just talking about, and that is the 7-kilometer resolution of the data set that went into your map, where the ice presence or absence at a given location is sensitive to things at like the 1 to 3 meter scale. And this question that you've described as lateral variability, because as you know, the average temperature of a region doesn't give you the average water ice at a region because it's so nonlinear, water ice is so nonlinear with temperature. What's the real meaning of what you're mapping, given that you're looking at such a different physical scale from the scale that controls the ice abundance or distribution?
I think the real meaning is that regionally, I think you don't want to look at this map pixel by pixel. I think you want to look at them regionally, and I'm deflecting the question to another scale. But you're looking at, nonetheless, some level of homogeneity at a regional level that's typically backed by the exposure of craters. The exposure of ice by fresh craters. So I hear very clearly what you're telling me. It works better than you would expect it does. Maybe that's my simple answer.
What measurements, mission, or something would you think it would take to validate a map like this?
Really high spatial, to validate it?
Yeah.
Probably a radar, something like that. Radio science, where you can see signal bouncing within a meter of the regolith with a high vertical resolution. Radar is probably the way to go to validate something like that. And then again, I'm hearing radar, clean ash and ice have the same, what's the electric, so I think we keep deflecting the answer to something else.
A shovel.
So that's how 1 meter was picked. You want something where you can shovel without breaking a backhoe, or, like a caterpillar or something. But yeah, you would have to go to a nice exposing crater to be guaranteed to be icy, I think.
Okay, thank you.
It's not super satisfying, I know. But it's probably the best I can answer.
Great. Okay. Bethany, Bruce, Sylvan, thanks for the wonderful discussion. Thank you for the talk. And we'll move on to our next.
I'm an IT guy.
So our next talk is Aaron Voss, and a follow-on with another talk on subsurface ice.
Great. Thanks, Sylvain, for the great introduction. So today, the second time today, I'm going to talk about the Martian. This time I'm going to talk about the Martian mid-latitude subsurface ice, which we think is a remnant of the past ice sheet that was deposited not very late ago. Of course, the motivation is super clear. We find ice in many locations. You've seen this plot several times today. But for me, it's even the motivation is even stronger because on the figure on the left, was for my last paper when I did my PhD. I did this super fancy coupling between the Mars PCM and a pore filling ice diffusion model, which I think I spent like 4 months on it. And eventually you can see that the diffusion model, the pore ice, and the observation does not fit. So I worked really hard. I rewrote a model. I ran simulations for the PCM for like few months, and eventually it doesn't fit the observation. So when Francois asked who wants to develop the subsurface ice scheme, I immediately jumped and said me, because now I will show the first application we use the subsurface ice to actually explain an observation. So we see the observation in Sylvain from before, and we can see it now from Colin Dundas. On the top, we have a map of crater ice. White means icy craters, and black means no icy craters, and we can see a really large longitudinal variation. And if we look on the bottom, on the right side, we have, on the bottom, we have the latitude, and on the right side, we have the crater diameter, the depths of the ice. And again, we see also a large variation even in the same latitude. Some of the ice can be 2 meters, and some can be half a meter, and many places where we don't have ice, and this is really was an enigmatic question for me. So we created the log layer scheme, which I already discussed, including many feedbacks into it. But this time I want to spend a second looking at the equation. We can see that the flux from the subsurface is controlled a lot by the depth of the ice and the QZ ice, which is the mixing ratio around the ice, which basically tells you at which temperature is the ice. So low thermal inertia means that less ice penetrate, and the ice temperature is closer to the mean. And it's also a strong function. It's also a strong function of the humidity, which is Q1 air. It tells you how much humidity you have in there, and then you have the difference between the amount of humidity in the air compared to the amount of humidity surrounding the ice. This you already seen. So here I show the first results. I show here just a snapshot of one of our runs. This is for latitude 45, obliquity of 25, and perihelion alignment of 270. And on the y-axis, we have the depths, and on the x-axis, we have the subsurface ice loss rate in millimeter per Mars year. And generally, we can see that as we are closer to the surface, the loss rate is higher, and as we we go deeper and deeper, the ice loss decreases significantly. Just note that both x-axis and y-axis are in a logarithmic scale. This is for different kind of humidities, each of the markers. And the black marker is a little special because it's for a different thermal inertia. This is for a thermal inertia of 150. So for instance, if we want to compare the thermal inertia of the black circle compared to the red circle, which is the same conditions beside the thermal inertia, we see that a lower thermal inertia results in a lower loss rate. We did the same trick again. I just show a snapshot here for different orbital parameters, which gives eventually different result because the temperature is different, the humidity is different, and so on. So here we show what is the ice loss as function of depth and orbital parameters and humidity. And if we will know the humidity and we will know what is the initial ice timing, we can maybe think of what is the evolution of ice since it was in place until today. So here is this figure looks simple and naive, but it's a nightmare because this compound out of about 80 different PCM simulation, 3D PCM simulation, where we calculate the humidity at each grid point, and we see it here in interpolation as function of time. At the top, we have the humidity in percipidal microns, and at the bottom, we have obliquity, and we can see how nicely they follow each other. I just want to point out, again, this is in a logarithmic scale. Obliquity 35 can lead to about 300 percipidal microns in latitude 45, while obliquity 18 can lead to about 2 or 3. So the difference is huge in humidity. Generally, higher obliquity and perihelion alignment of 90 leads to higher humidities. So this plot, I hope you guys recognize. I showed it once, Francois showed it once, and Joseph showed it like 5 times. This is the accumulation and the formation of the latitude-dependent Mendel. This is for obliquity 35 and LP of 90. And we can see that ice forms at around 45 degrees. Depends on the orbital exactly. You can move the red line up or down. The last time the obliquity was 35, it's around here. It's about 630 kilo years ago. And if we use all of the results I showed you until now, we can start the ice at 0 and let it evolve in time to see what is the final depth. And here I show several runs of different dust compositions. Different dust composition creates different depths, final depths, because as ice sublimates, the amount of dust left behind is different for different amount of dust. And the green one is the special one of 150. We also have results, of course, for thermal inertia of 50, of 350, and 40. This is, again, just a snapshot. But if we start emplacing ice 630 kilo years ago, we reach a plausible depth of, I don't know, 40 centimeters to 78 centimeters. And we can take it an extra step. We know the thermal inertia from measurement. I think this is from MCS, I'm not sure. Maybe I should put Sylvain Picard in 2025. And so this is the thermal inertia. If we know the thermal inertia also, we can measure for each location on Mars from 40 to 55, because this is what I calculated. What is the final depth? I just want to point out there's a really significant spatial variability in both latitude and longitude. We can see that we have 50 here, and just very close to it, we can have a thermal inertia of 400. So we did this exercise, and this is the final map we get for the subsurface ice final depths. And this is, of course, an interpolation, but we calculated in a resolution of 1 degree in longitude and latitude. And surprisingly, or not surprisingly, it really nicely fits the observation. So on the right, we have the ice depths, final depths in the color bars. The red line is the 7.5 water equivalent hydrogens for months, and the dots are, the white dots represent ice or maybe ice crater, and the black dot is craters with no ice, and next to it, wherever Colin was sure about the depths, I put the depths. And first I want to give you the impression of what is the variability, the large variability in longitude, very similar to observations. And it agrees with the observation very nicely, even better than I thought. So for instance, if we have a white dot, we want the final depths to be shallower, so it means that the crater penetrates to the ice. And if it's a black dot, we want the black dot depth to be shallower than the ice. Shallower than the ice, so the crater didn't reach all the way to the ice. So for instance, I don't know, can you see the numbers next to it? So for instance, here we got 0.77 and 0.6, and our model is 0.45. We also have location where we, for instance, here the white dot is 1.1, and our model is 70 centimeters, and next to it we have 0.26, which is great, so because we model 0.70. Even here, when we get 0.70, we get the ice is deeper. So basically, it matches the observation really nicely, maybe too good, so people won't believe me that is actually what I got as a result. The units on the right is the final depth of the ice, meters, sorry. Yes, meters. So 0.4 means 40 centimeters. We also did the same exercise, what happens if ice was in place 4 million years ago, when the obliquity was less 40. And the agreement with observation is less good, and we're very happy that it's less good because now we can constrain the timing of the ice, which actually really nicely match geological features. So we believe the ice is about 2 million years, maybe even less. I would say 630 because this was the last time it reached 35, obliquity reached 35 degrees, and until then it didn't reach higher. So to conclude, we developed a scheme in the Mars PCM to calculate the loss rate from the subsurface ice. Using this scheme, we wish to learn about the evolution of the polar cap layers, the mid-latitude ice, and the tropical glaciers. We quantitatively suggest that the mid-latitude subsurface ice are out of equilibrium remnants of past ice that is still slowly retreating today. Our simulation predict the flux strongly decrease with depth. The best fit between our modeled result and the observed ice depth suggests emplacement more recent than 4 million years, probably 630 kiloyears, aligning with geomorphical estimates of mid-latitude glacial events and Sylvain Piquet result, which is the best. And that the mid-latitude subsurface ice records the history of Mars past surface ice sheets, offering valuable constraints on the timing, extent, and decay of orbitally driven ice migration. Thank you very much.
Great, thank you, Aaron. And we definitely have time for questions, so I've got a mic, or come on down. Oh, yeah.
On your plot, you showed 1% dust content.
Yeah.
Content. Can you comment how the result would change with some change, or why did you pick that number?
I choose 1% because if you look at papers from Aditya Kuller, he suggests that the mid-latitude ice is almost pure and probably 1% or lower. We also, if you look here, we also have 2%, we also have 5%, 10%, but if you change it, it changes a little bit, so you can see the difference between 2 and 1 on 250 thermal inertia unit, which is a lot, and it's only 20%. So what happens when you have a higher dust, you bury it faster, and the flux decrease is faster. So if you can look in this plot, you drop to depths of 20, 30 centimeters quite quickly, and then it mellows down and becomes not flat, but almost flat. Thank you.
Nice analysis, Aaron. Question for you. Do you think that the mid-latitude ice deposits then are a one-time event? It was deposited and now it's disappearing, or do you think it comes and goes over time?
This is a very good question because I didn't say it. This is the top of the ice. I believe that below you have many different layers, and that some of them are being preserved over obliquity cycles and some are not. So I would say that if you, so I only calculate the top because I look on the less emplacement, but I'm pretty sure that below it you have many, many more layers of ice that has been preserved over obliquity cycle where it comes and goes.
Anna Grau here. So following up on that question, what has the change of the mobility of the ice have been throughout the Amazonian? Like, it sounds like you're losing mobile ice as you're burying it, right? Like, as you go through the different obliquity cycles, there's always a fraction of ice that remains buried,
I don't know if some can excavate completely. It depends on the amount of ice you deposit. Some can get lost completely if you don't have. So if you stay at a certain orbit all the time, ice will slowly sublimate until everything will be sublimate. But of course, as you change obliquity all the time, sometimes it's stable and sometimes it's not. I think you lose more and more ice, and this is also why I told you before that I believe that NPLD might be older, because it gets stuck there, and then to get it out when it's really deep, it's really hard. So.
Even the mid-latitude, not just the altitude.
Yeah, also the mid-latitude, and I believe also in the tropics. I think that it's just much deeper, and maybe it's out of our reach in our observational. I don't know enough about observations, but maybe it's out of our limitation to see it.
Jim Head, Brown University. This is really excellent. I just was thinking in our mapping of the latitude-dependent mantle previously, it was very clear that there are multiple layers. So yeah. The latest one, so it's very consistent with the thickness of the total layers. So I think it's really consistent with the latitude-dependent mantle in place over the past few hundreds of thousands to early millions.
Yeah, it's a good comment. I needed to say that this is only the top layer of the most recent ice, because I assume the ice was in place on the surface and slowly buried away. I'm pretty sure that if you look deeper, you can see more layers and remnants of previous.
And indeed, we also showed that at the lowest latitudes of the latitude-dependent mantle, it's being eaten away in this pitted terrain and returning.
Yeah, you can see it in this plot. If you look exactly. Here, it's much deeper than it's here, and this is not due to thermal inertia. This is due to lower latitude getting more insolation, and the flux is larger.
I have one quick question, if I could ask.
Sure.
So I see that this is submitted in revision, and I'm curious, when this is published, will you be releasing a digital data set of this data so modelers can take this and initialize their subsurfaces with ice?
First, I will do whatever the editor tells me to do for it to be published. This is the first thing. By general, this is a model. Person can run the model, and when you publish a paper, you usually give your results, and I can give them either as a figure like this or as fluxes, and people can interpret it the way they want. For me, once it's published, people can use it, and if they can make better science, I would be happy. Now it's in Nature Communication, Earth and Environment. I think this is the full name. But I'll send you an email once it will be published.
Very good, thanks. Okay, thanks again for the talk.
Thank you very much.
And our next talk is Mireille Kobayashi. It's our third and final talk on the subsurface water and ice. Take it away, please.
Okay, good afternoon, everyone. I'm Mireille Kobayashi, a PhD student at LMD and Tohoku University. Today, I'm going to talk about the shallow subsurface water distribution calculated with adsorption effects. As a reminder, let me begin with the water equivalent hydrogen. It's defined as a measure of water content in weight %, assuming all detected subsurface hydrogen is attributed to water molecules. The figure on the right shows the water equivalent hydrogen map derived by the Mars Odyssey neutron spectrometer. And this shows that significant amounts of hydrogen around the equator, such as 2 to 17 weight % at low latitudes. However, it remains unclear how the hydrogen is actually stored in the subsurface. Potential candidates should be subsurface ice, salt water, or OH groups bounded within minerals. So whether the hydrogen is accessible or not is an important question for future missions. Now I would like to mention about the previous numerical simulations of the subsurface water distribution. First, Luca Lange, 2023, suggests the subsurface ice is considered unstable on pole-facing slopes at latitudes lower than 30 degrees. And the other study shows that even the ice sheets formed during the last high obliquity period are predicted to be stable only for about 40 degrees and not near the equator. And absolutely, everyone's study should be included immediately in the slide. But taking together these modeling studies without seasonal ice nor absorbed water suggests that subsurface ice is unlikely to be the source of water equivalent hydrogen at latitudes lower than 30 degrees. Next, as also a reminder, I would like to explain a bit about adsorption. The Martian regolith has water absorbing property, and its absorbability depends on its physical characteristics. And on the right, we have the figure showing adsorbed water mass as a function of temperature and the water vapor density in the regolith. Clearly, we can see that the adsorbed water mass increases with decreasing temperature. And at low temperatures, adsorbed water mass is a function of the saturated water content. And also, the regolith of small grains has a large surface area exhibiting high adsorpting properties. This study has tried to estimate the water inventory in the shallow subsurface, taking into account both seasonal ice and adsorption, which increases as grain size decreases. So let me provide the overview of the model used in this study. The model consists of 3 parts. One is Mars Global Climate Model, just outputs, and 2 regolith model, the main model, and third is the regolith property model. The regolith property model, the second one, is uncoupled with the Mars Global Climate Model. Instead, it loads atmospheric variables at every 1 hour time step. Using these atmospheric inputs, the regolith model calculates diffusion, adsorption, and condensation within the subsurface. That calculation continues to 20,000 Martian years to obtain the steady state of adsorbed water. And the regolith property model determines the initial spatial distribution of regolith properties, and it executed only at the beginning of the simulation. So let me explain more about regolith model. The water in the regolith is classified into 3 states: water vapor, adsorbed water, and pore ice in the regolith model. And this model calculates water diffusion, adsorption, and condensation. And for diffusion, we consider vertical diffusion following Fick's law. And we have 2 diffusion mechanisms. One is Fick diffusion, and second one is Knudsen diffusion. And for adsorption, we adapted the adsorption and Thermo-Jakowski et al. 1997 for the basalt-like Martian analogs. And for pore ice, it forms when the local water vapor mass exceeds the saturated water content. And this regolith model, the resolution is, a horizontal resolution is 5.6 for latitude and longitude, and vertical layers, we have 20 uneven layers extending down to a depth of 20 meters within the regolith. Then regolith property model, we have 2 main regolith properties which affects the adsorbed water distribution. One is grain size. The distribution of grain size is determined by the nighttime thermal inertia derived from the thermal emission spectrometer observations. Here is the the equation is like that. And the second one is adsorption coefficient. The regolith adsorbability is defined by grain size. We have the theoretical equation, and there is a small amount of observations from the laboratory experiments. So combining these models, we consider two cases. One is homogeneous regolith property, and the other is the inhomogeneous adsorption coefficients are tested in this study. So let's move on to the results. We have the maps, two maps of spatial distributions of the grain size on the right, on the left, and the adsorption coefficient on the right. For grain size, most regions exhibit grain sizes between 100 to 1,000 microns. However, the areas with low thermal inertia clearly show very fine grains, less than 5 micron. And on the right, adsorption coefficient typically ranges from 5 to 8 kilogram per cubic meter in most regions. But as you can see, it increases to around 170 kilogram per cubic meter in the regions of small grain size, like 5 microns. And let's examine the distribution of adsorbed water in the case of homogeneous adsorption coefficient. Here we have the total a map of total adsorbed water mass integrated to a depth of 1 meter below the surface. The adsorbed water mass ranges from 0.05 to 2 kilogram per square meter, which corresponds to 0.003 to 0.1 weight percent for water equivalent hydrogen. And we can see the northern hemisphere exhibit higher adsorbed water mass than the southern hemisphere. This is because the atmosphere has plenty of water vapor in the northern hemisphere. And second one is that adsorbed water mass increases towards 50 degrees in the north and 60 degrees in the south from the equator. Let me explain more about the temperature effect. Here we have the correlation between temperature and adsorbed water. And with dashed lines, it represents the adsorbed water contents calculated with the saturated water contents. As temperature drops toward 195 Kelvin, the adsorbed water mass increases. In regions colder than 195 Kelvin, the adsorbed water content matches that of the saturated water content. Since the water vapor mass is also a function of temperature, this demonstrates that the temperature is a primary factor limiting the maximum absorption rather than the water vapor mass in the regolith. And next is in the case of inhomogeneous regolith. Here you have the spatial distribution of the adsorbed water integrated to a depth of 1 meter. And here we have the 0.02 to 1 kilograms per square meter in most regions. For we consider the inhomogeneous regolith based on the grain size. The adsorbed water mass is 0.6 weight percent at most around mid C4C, more than 1 order of magnitude less than the weight, water equivalent hydrogen. So let me mention a little bit about the polar ice. Here we have three vertical distributions of zonal mean pore ice mass, and also annual mean. And pore ice mass increases towards high latitudes, as you can see. From the left, we have homogeneous, inhomogeneous, and the differences. And stable subsurface ice clearly exists pore walls of 60 degrees north and 60 degrees south, and there's no ice in low and middle latitudes. And when we look at the seasonal ice increases in regions of high absorbability in shallow layers. When you look at the differences on the right figure, in this case, homogeneous regolith has higher absorbability in the shallower layer. In the high latitudes, so the absorbed water accumulated in summer turns into pore ice in winter. So the highly absorbed regolith holds more water in the subsurface, and the state is changeable between the adsorbed water and pore ice. So, and our results have several implications for the absorbed water equivalent hydrogen in the lower latitudes. Although the absorption coefficient has large uncertainty due to the lack of observations, and the absorbed water mass calculated with the absorption isotherm of the Martian analog is still too small to explain the water equivalent hydrogen. This indicates that a large portion of this kind of hydrogen is stored within hydrous minerals. But if a significant portion of the water equivalent hydrogen is adsorbed water within the hydrous minerals, it might be more easily accessible for future missions. And in this work, for future work, we propose incorporating the spatial distribution of smectite and utilizing its specific adsorption isotherm for hydrous minerals. That's conclusion, and that's all my talk. Thank you very much.
Thank you, Mireille. Questions?
Hi, Mireille. Eran Vossel, MD. I have a question, maybe a naive one. How much of the water is breathed during the night and day from the absorption phase? From the regolith to the atmosphere and back to the atmosphere, back to the regolith.
Approximately 1 precipitation micron for daily.
Is it a function of latitude, longitude, or?
Yes, of course.
How much in the tropics?
Sorry, what?
How much is in the tropics approximately? Also 1 precipitation?
Yeah, I mean 1 precipitation micron at the maximum. Yeah, so.
Thank you so much.
Thank you.
Hi, Bruce Tchaikovsky, University of Colorado. For calculating the adsorption isotherms, what
composition
of the regolith material?
It's based on Zenta-Tor 1995, so basalt like Martian analog, I think. So it's not non-hydrous mineral.
Yeah, I think once you go to more clay-like material with higher adsorption abundances, you'll get much closer to the water equivalent hydrogen amounts. This is really important work, trying to understand how much water.
Thank you very much. When I think about the hydrous mineral, it takes time to reach equilibrium between the water and vapor and adsorbed water. So that mechanism should be included in the model, I think.
Adam Valentina, CTH Zurich. Great work, really interesting So many comments I can make, but I'll just focus on a few maybe now. So we know from orbital observations that there are no smectites in Medusa fossae. It's very spectrally neutral. You don't see any near-infrared absorption features due to OH or H2O. There's a 3-micron band, but on Mars, 3-micron band is almost everywhere. So I was thinking, what if you used not smectites, but something of a Martian dust simulant that we have produced recently, which is basically incorporates basaltic powder and iron hydroxides. Would that be useful actually for you?
Thank you very much.
Hi, Niar. I have a question. We discussed together about the validation of your model at landing sites, and notably comparison with Phoenix, MSL, and M2020. Your model, so you have included the near-surface frost and the subsurface. Does your model predict subsurface frost at MSL or M2020 landing sites? I think it's a good pre-value because the papers by Savijarvi doesn't model subsurface water ice. It might be relevant for people in this mission who are looking at that actually. Do you have an answer for that? Do you have frost forming on this landing site during the night, for instance?
Yes, we have subsurface frost at night, but it turns to adsorb water in the daytime.
Okay, thank you. Great. Yes.
Thank you very much.
Okay, our next speaker is Yangcheng Luo, who will take us out of the surface, I think, right, and a little up into the atmosphere to look at oscillations in composition and oxidation. And this is our keynote speaker for this session. So you get an extra 5 minutes, and take it away.
Good afternoon, everybody. I'm happy to give the last talk of today before we board our boat to enjoy the French cuisine. My name is Yangcheng Luo. I'm a postdoc at LMD. I work with François Faget and part of the ERC Mars Through Time team. First, I would like to thank all my team members. They are really helpful and really reliable, and it's really a good experience to work in such a team. So this project is funded by the European Research Council. Okay, so I have some extra minutes, so I'd like to give some basic concepts of atmospheric chemistry so that everybody in this room can be on the same page. For Mars, we have this kind of atmosphere on the present-day Mars. 95% of the atmosphere is made of CO2. And CO2 is condensable. It has an inventory in the polar CO2 ice caps. And for the rest of 5%, we have nitrogen and argon. And they made up most of the rest of 5%. And in the last bit of the atmosphere, we have a lot of species, chemical species, including molecular oxygen, carbon monoxide, water vapor, and hydrogen peroxide, which is also condensable. Water vapor is also condensable, of course, and it has the inventory in the polar water ice. And we have hydrogen, we have ozone, which is observable, we have nitrogen-bearing species, and we have a suite of radicals. Oh, okay, sorry. Yeah, we have a large number of radicals which have trace amount in the atmosphere but play a key role in the atmospheric photochemistry. These include OH and HO2, atomic hydrogen, atomic oxygen, and nitrogen atoms. And we also have the controversial methane and chlorine-bearing species and some noble gases. Among these, there are several long-lived species. I say they are long-lived because their chemical destruction is quite slow compared to their transport timescale, so that in the atmosphere, they are mostly uniformly distributed, uniformly mixed throughout the atmosphere. These include CO2, hydrogen, CO, and oxygen, and noble gases. And we also care about them because they can comprise the major compositions of the atmosphere because they are long-lived. The short-lived species have no chance to become major components of the atmosphere. And it's hard to model these long-lived species because with sophisticated models like the Mars PCM, for several months, we can maybe finish several decades of Mars years. And for the long-lived species, their lifetime can be easily longer than that, and which is beyond our capability. So previous studies mostly focused on the short-lived species like ozone and compared the results with observations. And in this talk, I'm going to present my simulation results for the long-lived species. Before we get started, I will introduce some basic concepts in the Mars photochemistry. The Mars photochemistry started from CO2 photolysis by UV radiation, with wavelengths shorter than 205 nanometers. And following that, the produced atomic oxygen can react with itself to form molecular oxygen. Molecular oxygen is not the ultimate sink for O, because molecular oxygen can also be fertilized back into atomic oxygen. So combining the two reactions, we get this net reaction. So 2 moles of CO2 can be fertilized into 2 moles of CO plus 1 mole of molecular oxygen. However, the reverse reaction of this, the reaction in the red box, is very slow because it's spin forbidden. So we would expect that after a long time, a large quantity of the CO2 in the atmosphere will be fertilized and forms oxygen, molecular oxygen and CO in the 1:2 ratio. Previous one-dimensional model predicted that under this scenario, when we have no other tracer, no other elements in the system, we would expect 8% of the atmosphere is made of CO and 4% will be made of oxygen. However, this is really different from what has been observed. The observations tell us that there's less than 1 per mil of CO in the atmosphere, and about 1 per mil oxygen in the atmosphere. So this poses the CO2 stability problem, the first classic problem in the Mars photochemistry in the 1970s. Then there was a great theoretical breakthrough in the 1970s when people realized that some trace amount of radicals can serve as catalysts to convert CO back to CO2. So this starts from the photolysis of water vapor, and water can be fertilized into H and OH by UV radiation. And you may notice that the UV photons here are the same UV photons that fertilize CO2. So if we have more CO2 in the atmosphere, there can be UV shielding by the CO2, which protects water vapor from being fertilized. And the produced atomic hydrogen can then combine with molecular oxygen to form HO2. And now we have the 3 members of the odd oxygen family, which is also called HOX, which include H, OH, and HO2. And they are the most important catalysts in the Mars photochemistry. So how do they convert CO back to CO2? There is one pathway. So CO, instead of being fertilized, instead of being destroyed by O atoms, CO can be destroyed by OH radicals to form CO2, and H is left behind. Then we need to convert the H back to OH to conserve the quantities of the tracers of the catalysts. So H can then react with molecular oxygen to form HO2, and HO2 then react with atomic oxygen to form H. If we sum these 3 reactions together, we get the net reaction. CO plus O forms CO2. So this is how CO is converted back to CO2. And this also tells us that water vapor plays a key role in the photochemistry because the photolysis of water produces the HOX radicals, which act as catalysts. So when we go back through time, we see that Mars has undergone drastic obliquity variations. And from the many talks today and in the past few days, you know that at different obliquity, Mars has different water content in its atmosphere. So the obliquity variations are expected to affect photochemistry because they control the atmospheric water content. So at higher obliquity, we have the polar regions receive more solar insolation and warm up, which injects more water vapor into the atmosphere. And then, during this process, as Joseph Nahr talked about, we updated the microphysics of water cloud in the model so that the water cloud droplets particles can grow to larger size, which causes a greenhouse effect. And this can further amplify the warming of polar regions at high obliquities. And then we get faster water vapor photolysis, and we get more HOX in the atmosphere. So the model we use is the Mars Planetary Climate Model, PCM version 5.5. We can model the whole atmosphere from the surface to the thermosphere, and we use the radioactive water ice cloud and cloud microphysics a feature in the version 6. But we use a simpler treatment for dust. So we prescribe dust opacity to certain Mars year observations or to certain opacity values. We have so many neutral species and charged species, and we have many, many reactions, including the reactions on heterogeneous surface, for example, on water ice cloud or on dust. But on dust, there's a switch, we usually turn it off. And these heterogeneous reactions can remove HOX from the atmosphere. And I will show their effect later. So before we move on to the other obliquities, we first need to verify that our model behaves well when simulating the present-day Mars atmosphere. So we use the model to revisit the CO2 stability problem. From my introduction earlier, you may have an impression that the CO2 stability problem has been solved, but in fact it's not. So following the 1970s, the works in 1970s, people first produced too much CO in the atmosphere compared to observations. And they tried different methods, for example, raising water to higher altitude to get more water vapor photolysis and destroy CO. But later in the 1980s, they realized that the cross-section of CO2 is temperature dependent. When we want to model Mars, we need to extrapolate lab data to very cold temperatures. So at cold temperatures, the CO2 does not absorb UV very efficiently, which means that more UV can photolyze the water vapor and produce the catalysts. And then people found that these catalysts convert too much CO back to CO2. And then the model CO becomes smaller or less than the observations. So this is the CO deficit problem since 1980s. And these are the observations of the present-day annual mean global mean CO concentration on Mars. The highest value is given by the ACS solar occultation measurement, 960 parts per million. And the lowest one is given by the Curiosity rover, 580 parts per million. The average value between these instruments lies between 800 and 900 parts per million. So this is our goal. What about the previous models? Previous one-dimensional models, the standard models using standard reaction rates and the standard treatment of the water, they produced only 120 to 140 parts per million, 80% lower than the observations. So then we use our Mars PCM to look at this problem again. We find that in our simulations, there's some natural variability in the water vapor content in the atmosphere, even when driven by the same dust scenario, which causes it very difficult to determine whether CO has reached equilibrium, because CO is always changing year by year. So we first ran the model for many years and get a relatively stable water cycle, and we pick 1 year with a medium water vapor loading to drive the photochemistry in the model. And we also set the mixing ratios of hydrogen and oxygen to the observed values because the CO-CO2 problem is essentially a redox problem, and H2 and O2 play a critical role in setting the redox state of the atmosphere. And we use the standard resolutions. Then we get 740 parts per million, which is already close to the 800, 900 parts per million observed values. This is there is a great improvement compared to previous 1D results. And after tuning some important reaction rates by their lab experiment era, we find that we are even closer to the observations. And sometimes we can overshoot. For example, if we add the destruction of Hawks on dust particles, we get 6,000 parts per million, six times higher than the observed. Which means that it's no longer difficult to reproduce the observations with our model. And we also looked at what contributed to this improvement. We find that two additional processes in our model. One is the heterogeneous Hawks loss on water ice, and the other is the condensation and deposition of H2O2 contribute about 100 parts per million to the results. And even without these two processes, we can compare our model with previous 1D model, and we can already see a great improvement. So that's the findings. Okay, but I do not claim that we have fully solved this CO2 stability problem, because while we have solved the CO deficit problem, we created another problem. Our model now produces a weaker oxidizing capacity than previous 1D models, which elevates all the reduced species, including CO and hydrogen. Well, CO was previously modeled lower than the observation, so now our CO matches the observation better. But for hydrogen, modeled hydrogen concentration was already a little higher than the observed. So after we upgrade to the three-dimensional model, we produce much more hydrogen than the observations. Now we produce about 300 parts per million hydrogen, 20 times higher than the observed. So then solving the CO deficit problem and the H2 surplus problem at the same time is more challenging because it requires some more structural tuning. And these issues and other issues, including the underestimated ozone and curiosity's observed seasonal O2 variations and the puzzling methane, reveal gaps in our current understanding of Mars atmospheric chemistry. So we need more observations to constrain the concentrations. Okay, now we can move to the other obliquities. So for the experiment, we use a much coarser resolution in order to get faster results. We will refine the resolution later. And we set the visible band dust opacity to 0.2 at 610 Pascal level. And we set orbital eccentricity to 0. And we explored obliquities between 5 degrees obliquity and 45 degrees. So these are the results. The first figure shows the annual mean, zonal mean temperature, surface temperature as the function of latitude. And we can see that at 5 degrees obliquity, the polar regions are much colder than the present day. It's less than 120 Kelvin. And at higher obliquity, we have much warmer polar regions. Because of that, the second picture shows the pressure of CO2 in the atmosphere. So right now at 25 degrees obliquity, we have the 610 Pascal. But when we move down to 5 degrees obliquity, we have 1 order of magnitude less CO2 in the atmosphere. If we move to higher obliquity, we find that all CO2 ice, as Luca mentioned today earlier, all CO2 ice sublimates, so we have no CO2 ice, and all the CO2 is in the atmosphere. For water vapor, that's the third picture. We see that the amount of water vapor in the atmosphere changes by many orders of magnitude when we change the obliquity. From present day to 5 degrees obliquity, it changes by 2 to 3 orders of magnitude. And to higher obliquity, it also changes by 1 or 2 orders of magnitude. So we find that as we change the obliquity, because the water vapor content in the atmosphere changes, the water vapor photolysis rate also changes a lot by many orders of magnitude, which results in oscillations of OH concentration in the atmosphere by many orders of magnitude. Because OH is the strongest oxidant in the atmosphere, so this implies that the oxidizing capacity of the atmosphere changes a lot when the obliquity varies. And as a result, CO, as the reduced species, can have different lifetime and is destroyed at different rates. So at higher obliquity, we have much less CO because it's destroyed by OH. We have only 10 ppm of CO, but at low obliquity, like 15 degrees, we have much higher CO concentration, 4,000 ppm. That's almost 0.5%. And we asked two questions, one for the high obliquity and the other for the low obliquity. For the high obliquity, we asked, is there too much hydrogen peroxide? So hydrogen peroxide is produced ultimately from water vapor photolysis. And at high obliquity, we have much faster water vapor photolysis, and it can produce the HO2, and HO2 can react with itself to form hydrogen peroxide. Why do we care about hydrogen peroxide? Because they can condense onto the surface and potentially oxidize organic materials and removing any potential biosignatures from the past. And this is, if we change obliquity from 5 to 25 degrees, we can surely see an increase in the hydrogen peroxide concentration. However, we find that at high obliquity, something is suppressing the hydrogen peroxide concentration. We don't see a very high concentration of hydrogen peroxide at high obliquity. And this is mainly because that the production of hydrogen peroxide through by HO2 is much stable. This rate is much stable across obliquities. And also at high obliquity, because we have a lot of OH in the atmosphere, it can also destroy hydrogen peroxide. So hydrogen peroxide concentration is actually lower at high obliquity, and it peaks around the present-day obliquity of 25 degrees. For the low obliquity Mars, we ask another question. Can we have a CO-dominated atmosphere? We expect this because at low obliquity, there's much less water, so there are no catalysts, so CO2 can be photolysed into CO, and CO cannot return to CO2. But, and this is what we see when we decrease obliquity from 45 degrees to 15 degrees. But if we go to lower obliquity, we get less CO in the atmosphere. And this is because we have less CO2 in the atmosphere, so the shielding effect of UV by CO2 is much weaker, and more water vapor can be exposed to UV radiation and get photolysed. So we get much more. In fact, we get more OH in the atmosphere, which can destroy CO. So CO concentration is lower at ultra low obliquity, and there was never a CO-dominated atmosphere in the recent past. Okay, to summarize, our PCM can now reasonably reproduce the present-day CO observations, but we created another H2 surplus problem, and atmospheric water content and oxidizing capacity oscillates with obliquity, and there is no excessive hydrogen peroxide at high obliquity, and there was no CO-dominated atmosphere in the recent past. There are some remaining problems. For example, how does molecular hydrogen change with obliquity? It's difficult to model this because the chemical production and loss of hydrogen is quite slow. And if there's any artifact production, like non-conservation of hydrogen in the model, it can easily overwhelm the signal. And also, at high obliquity, we may expose more buried CO2 ice and water ice to the atmosphere. And the last question I would like to ask this community is, can the surface be oxidized by OH and H2O2? Because the answer to this question will affect our conclusions. If OH mainly oxidizes the surface, then the surface can be mostly oxidized episodically during high obliquity. But if H2O2 oxidizes the surface, then the oxidation becomes much stable over different obliquities. Thank you.
Thank you, and here come the questions. Okay.
Thank you, Yang Cheng. That was very insightful. I really enjoyed seeing how, you know, everything works against and for everything else, and you made some very compelling arguments for why behavior will change as obliquity changes. My question is, for the CO deficit problem, you noted that in your model you were using what you said was the Curiosity O2 measurements, and then a few slides later you noted correctly that those vary significantly by season. It's a very peculiar cycle, I guess. So my two questions are, what value did you use, and did you explore the sensitivity to the high and low parts of that range?
I didn't, for the curiosity value, I think I used the 1,560 parts per million. That's reported in the Trainer et al. Paper as the annual mean oxygen volume mixing ratio at curiosity site. I also explored a lower oxygen mixing ratio reported by previous space telescope observations. That's 1,400 parts per million. 10% lower than the Curiosity rover values, and as a result, I get 10% more CO in the atmosphere. I didn't explore the upper bound of the Curiosity values. I only explored the effect of these two values.
Thank you.
Thank you.
Adam Valentin, CTH Zurich, super exciting, very interesting work and a very interesting question. So looks like it's been, in the conference, it's been emerging that H2O2 is, or hydrogen peroxide is not a good candidate, because also from, you know, the previous talk that we saw a few days ago about warming of ancient Mars, it's H2O2 is not, you know, it's not a good candidate. And also from the lab experiments that we have been employing, when we're oxidizing iron-rich aqueous solutions using H2O2, we end up with minerals that are not observed in large quantities on the surface of Mars. So, so I think there is a lot of potential to explore the OH direction, and I think we can definitely talk about this, and I think in a year we might have some also very interesting results as well coming from the lab at ETH Zurich. Yeah, thank you.
Thank you for the comment.
Sorry, I've got a question. So from previous talks, is this on? Yes, from previous talks on obliquity changes, we saw that those can have a large impact on the water cycle. In particular, it can change the abundance of water ice clouds. And so my question is about heterogeneous chemistry, and in the cases where the obliquity can ramp up the abundance of these water ice clouds, how important do you think heterogeneous chemistry on those water ice clouds could be with respect to all your results here? How could it perturb that and maybe either improve or drive the solution away from what you're trying to reproduce?
That's an important point. So the heterogeneous reactions in our model mostly removes OH, HO2, and hydrogen peroxide from the atmosphere. On the present-day Mars, at the present-day obliquity, they play a minor role, not negligible role, but minor role. At high obliquity, I would guess that the water vapor photolysis produces a lot of HOX species, but these heterogeneous reactions can remove some of it. But I would like to note that at high obliquity, we have much more cloud, that for sure. But we have larger cloud droplets. And so the surface area, the total surface area, may not increase as the amount of cloud increases. Yeah.
Thank you, Yang Chen, and very nice introduction of atmospheric chemistry for me, physical guy. And My simple question is that I'm wondering that if you mentioned that the CO2 carbon dioxide will serve as the shield for the UV, how to say that, the transformation from the H2O into hydrogen atomic into H. So I'm wondering if in the history, if the atmosphere of the Mars is denser, will there be holding more waters? Because the water will be less possible to lost to the space.
So in the past, when the atmosphere was denser, and the CO2 can protect water from being fertilized. So
is that possible?
Yeah, I think that's possible.
Okay, so things like serving as like ozone on the Earth. Is this kind of analogy make sense?
Yeah, so I remember from a talk 2 days ago, there was result that at high surface pressure of CO2, there can be a CO-dominated atmosphere. I think that one of the reasons is that CO2 then protected water from being fertilized. So the catalysts in that atmosphere were very tiny amount, so CO could not be efficiently converted to CO2.
That makes sense. Thank you very much.
Okay, I think we'll wrap up the session then for today, and thank you to our 4 speakers in this session for their really excellent talks. It was very interesting, and thank you. All right. Any other announcements? No. You are all free to go. Fly and be free, and get ready for the boat ride. All right.